One that's already out in collaboration with Mauricio Romo and Emanuel Scheidecker, which came out in March, and another one with my student David Erkinger, which is still in progress. And what we are doing is we're using supersymmetric gauge theory. So to be more precise, two-dimensional gauge linear sigma model and fairly recent results from supersymmetric localization to study the stringy Kahler moduli space and sort of universal structures in the stringy Kahler moduli space. So this is the outline of my talk. I will start off with an overview, which will take me quite a lot of time. This is sort of the executive summary of the talk. And the remaining time I will use to fill in the details, which will be to recall the gauge linear sigma models and the results from localization, in particular the hemisphere and the sphere partition function. And then I will discuss in more detail the results we have found in our paper on how general structures of the hemisphere partition function evaluated in certain phases of the gauge linear sigma model look like. All right, so let me start with setting the stage. What I will discuss today is the stringy Kahler moduli space. And in this talk, I will confine myself to general setting of Calabi-Yau threefolds in a type 2 string theory with or without D-branes. And I also want to mention at the beginning that I will have a rather broad notion of what a Calabi-Yau threefold is. In particular, I will not make the assumption that it is somehow geometric, but I will view it a little more abstractly as an example of a 2,2 superconformal field theory with central charge 9. So what I've tried to draw here is a cartoon of what the stringy Kahler moduli space looks like. So since we are looking at Calabi-Yaus, what we have here at every point in the moduli space is a superconformal field theory. The point is that there are usually quantum corrections, and at a generic point in the moduli space, we don't really know how this superconformal field theory is realized concretely. But if we go into certain limiting regions in the moduli space, then we know very well what these superconformal field theories look like, at least in some regions. And the best studied examples are, of course, the large volume regions in the moduli space, where you indeed have some geometric description of your Calabi-Yau compactification. And the conformal field theory is realized in terms of a non-linear sigma model with Calabi-Yau target. On the other hand, there are other limiting regions in the moduli space which are not like that. And well-studied examples are, for instance, Landau-Ginzburg orbifold regions, which can be somewhere else in the moduli space, and they are not really geometric in the sense of a nonlinear sigma model. And actually, the generic points in the moduli space are usually neither large volume nor Landau-Ginzburg, but are some kind of hybrids thereof. And those are not really well understood. And depending on which region you are, there are sort of boundaries where the properties of the theory change. So the Kahler moduli space is divided up into chambers. And actually you can cross between these chamber boundaries to go from one locus to another. And usually something happens to the Calabi-Yau. So you don't even need to have the same Calabi-Yau. There can be some kind of topological transition taking place. And then you have more than one Calabi-Yau sharing the same Kahler moduli space. And for instance, you can go from the large volume region to a Landau-Ginzburg region, and that would be the famous Landau-Ginzburg Calabi-Yau correspondence. And you can ask the questions, okay, how are the theories in these chambers corresponding to these chambers related? And I guess the most general and also mostly conjectural statement is that certain categories, D-brane categories associated to certain Calabi-Yaus and limiting regions are equivalent. And what I want to do in this talk is to study limiting regions in the Kahler moduli space which are not of the large volume type. And the physics tool I'm going to study the gauge linear sigma model. So a 2D 2,2 supersymmetric gauge theory. And in the context I'm using it, the important fact is that the GLSM provides a common UV description to all the CFTs that you have along the Kahler moduli space. And the way the GLSM does it is that the chambers are realized, or the physics in the chambers is realized as low energy configurations of the gauge linear sigma model. And to see how this works, we have to note that being what it is, the gauge linear sigma model comes with certain parameters, and in particular, it comes with Fi theta parameters. They're complex parameters. I denote them by T. Theta is the Fi parameter, theta is the theta angle. And they can actually be identified with coordinates on the Kahler moduli space. So by studying the gauge linear sigma model at different couplings, we can get access to the different regions in the moduli space we are interested in, and not necessarily the large volume regions. And actually the GLSM, of course, when you study the different coupling, can behave differently at low energies, and that realizes these chamber structures I had on the picture of the previous page. So the upshot is we can use the gauge linear sigma model to map out the Kahler moduli space of a Calabi-Yau. So this is actually a rather old story. What has been developed more recently is that you can apply methods of supersymmetric localization, of course, also to the gauge linear sigma model. And what you get is exact supersymmetric partition functions. And I will show what they look like a bit later. What I want to stress now is that the partition function you get, you can evaluate them in different phases. And this way you can actually access different regions and compute whatever these exact partition functions compute. And in particular, you can also compute quantum corrections with them, because technically these partition functions will depend on the Fi parameters, and the parameter dependence on those will translate into the worldsheet instanton corrections you have in these theories. So it's possible to use the GLSM to compute quantum corrections in string compactification directly within the context of the supersymmetric gauge theory. All right, so my plan is now to study what these partition functions look like when we are not in geometric settings. And for this, I also want to recall that geometric regions in the modular space are, of course, very well understood, and we know very well how to do computation, because we have a lot of tools like toric geometry, topological string theory, mirror symmetry. We know how to compute enumerative invariants, which correspond to these instanton corrections, and so on. And there are many reasons to believe that the structures that we see in geometry, they also hold at other loci in the modular space. And well, arguments in favor of this is of course the worldsheet CFT, which does not really care whether there is a geometric space-time description of itself. And also the results of supersymmetric localizations indicates that whatever you compute in non-geometric phases cannot be as so much difference to the geometric setting, because you have this, all of it has the same UV origin. So the question we asked ourselves in our papers was, if we evaluate these partition functions in generic phases of gauge linear sigma model, how do we interpret the results in the IR theory? And what we found is that when we do that, the results, the quantum exact results in the phases have actually the same structure in every phase. And in order to uncover these structures, you need something that is, or objects that are available beyond geometric settings. And actually, if you look in the literature, there's quite a lot that you can find. So a lot of information, of course, you get from the worldsheet CFT, from topological gravity, and structures like TT star geometry. Also, when it comes to enumerative invariants, there is FJRW theory, Fan, Jarvis, Rahn, and Witten, who developed tools for enumerative problems in theories that are not necessarily geometric. There are also certain mirror constructions which do not necessarily depend on geometric properties, like for instance, Giventhal's mirror construction, which will play a role here in this talk. And when you consider D-branes, of course, also categories are general enough in order to capture D-branes beyond geometric settings. And we studied the hemisphere partition function and the sphere partition function, and we find that certain ingredients appear in every phase when we evaluate these partition functions. And these are a certain choice of state space and the pairing, the I and the J function, which come from Giventhal's mirror construction, which essentially encode the instanton corrections of the result. Then there is some topological information in terms given by the gamma class. And if we have D-branes, there's additional data from the D-branes. So let me, in one slide, show you what we found. We conjecture that when we evaluate the hemisphere partition function in any phase of a Calabi-Yau gauge linear sigma model, it always has this particular form. We have a pairing, we have a Chern character of a brane, we have the gamma class, and we have the I or the J function. I will say a little bit more about I versus J function later on. And we have shown this in geometry, where many results were already known, but also in Landau-Ginzburg-Orbifold phases. And similarly, in the work in progress with my student David, we tried to do the same thing for the sphere partition function. And we also find a structure like this. The I function and its complex conjugate makes an appearance, but our results show that complex conjugation is actually a bit more complicated than expected, even though that the structures we see here can actually be found in the literature. So there's also, again, the gamma class and the grading operator acting on the state space making an appearance. And we actually tried this for hybrid type phases, which are Landau-Ginzburg-Orbifold fibered over some base manifold. So this is the main results. That's actually all I wanted to say. And the rest of the talk will be to fill in the details. We will proceed as follows. At first, I will recall what the left-hand side of these equations are, and then I will move on to discuss a bit what the objects on the right-hand side are. Okay, I apologize for the slightly technical slides. I will not introduce the full gauge linear sigma model, but only those aspects of it that I will need to define the partition function. And that includes G, which is the gauge group, a complex vector space where the scalar components of the chiral multiplets take values, a corresponding matter representation, and at this point, actually, the Calabi-Yau condition enters. So I will have a stronger restriction on the type of matter representation I can have, and that translates into the cancellation of the axial anomaly in the gauge linear sigma model. We have R symmetry because it's a 2,2 theory, and I will need the vector R symmetry and the corresponding R charges of the fields I will call Ri. And furthermore, I will choose a maximal torus because in principle, this gauge group can also be non-abelian. And the corresponding Lie algebras. And then the gauge charges of these chirals take values in the dual of the complexified Lie algebra of the maximal torus. And I will denote them by Q, and the index I labels the field, and the index A labels the U1 inside the maximal torus. Okay. Furthermore, I need to introduce the Fi theta parameters that I have mentioned before. And we also have scalar components of the vector multiplet of the gauge linear sigma model, which I will denote by sigma A. And you see here that there is actually a natural pairing between the T's and the sigmas because they take values in the duals of the corresponding Lie algebra. And I will actually discuss exclusively compact Calabi-Yaus, compact Calabi-Yau threefolds in my discussion. So in order to model that in the gauge linear sigma model, I also have a non-zero superpotential, which is G invariant and has R charge 2. And yeah, so different GLSMs will then correspond to different Calabi-Yaus. And since I will talk about the hemisphere partition function, I will also introduce D-branes. So I will look at B-type D-branes, so certain BPS D-branes that break half of the supersymmetry. And they have a very nice and very non-geometric description, actually, in the gauge linear sigma model in terms of matrix factorizations. So the data you need to describe a GLSM D-branes is a Chern-Patten space, which is a set2 graded module, and then a matrix factorization, which is an odd endomorphism on this space. And matrix factorization means that you have a square matrix, which I denote by Q, which has entries in terms of these chiral fields phi. And the condition is that it squares to the superpotential I just introduced times the identity matrix on M. And because we have a gauge symmetry and we also have an R symmetry, these symmetries are also acting on the D-branes. So what we have is that the D-brane should be gauge invariant. This is this condition here. And it defines, in addition to the matrix factorization, another matrix row that given a Q, you can just compute by solving this condition. And similarly, we also have R symmetry acting on the brane. And because I just told you that the superpotential has to have R charge 2, by this condition here, the matrix factorization or the matrix Q has to have R charge 1. And this is encoded in this condition. So the upshot of that is what we will need later on is we have the D-brane data is a matrix factorization, but also these two matrices rho and R star, which encodes the R charges and the gauge charges of the D-brane. Okay, and also here, different matrix factorizations correspond to different branes. So with that, I have all the ingredients to recall what the sphere partition function is. So what we have here is, so this is when you take the gauge linear sigma model, you put it on a sphere, and you exactly evaluate the path integral, it localizes onto this expression. And what we have here is a normalization constant, a sum over an integer lattice, which comes from the fact that the gauge field on the sphere takes discrete values, an integral over the maximal torus of the GLSM, parameterized by the sigma fields. If you have a non-abelian gauge group, you have this factor here where alpha are the positive roots, and this notation here with the parentheses, this is this pairing between the Lie algebra and its dual that I have mentioned before. The information about the chiral matter fields enters here in this quotient of gamma functions, and the Q's and the R's are just the gauge and the R charges of the fields that I have introduced before. And furthermore, importantly, there is an Fi parameter theta and the theta angle appearing here. So this is what you get in the gauge linear sigma model. So if you now want to go to a phase, what you have to do is you have to evaluate this integral. And this is a multidimensional complex contour integral. Gamma here is an integration contour that you have to choose in such a way that all poles are avoided. And in the end, the choice of phase is given by the value of this theta and theta. So large or positive or something like that. And depending on this value of theta here, you have to get a convergent result in the end. So you will have to close your integration contour in a certain way. And that will actually enclose, depending on the value of theta, different poles of these gamma functions here. And that's why the result, depending on the value of the Fi theta parameter, will be different. And that's how you get from the sphere partition function of the gauge linear sigma model to the result in the phases. And we actually know what the sphere partition function computes. It's a very interesting quantity in the context of string compactification. It's the exact Kahler potential on the Kahler moduli space. So it can also be used, for instance, to extract chromophytin invariants from these expressions. And the hemisphere partition function is actually very similar. So you've seen these structures before. Here is again the Fi theta parameter, now with a somewhat easier dependence. And the hemisphere partition function is evaluated for a particular B-type D-brane at the boundary, inserted at the boundary of the hemisphere. And all the information of the D-brane is hidden or is encoded in this factor B, which I call the brane factor. And if you have a matrix factorization characterizing the brane, and you automatically get these matrices R and rho encoding the gauge and R charges of the D-brane, you can explicitly evaluate this brane factor and then go on and evaluate this contour integral in the phase of the gauge linear sigma model that you're interested in. And also this computes some interesting quantity, namely the exact D-brane central charge. So these are the definition of the sphere and the hemisphere partition function. And the rest of the talk will now be dedicated to discussing of what these expressions look like in certain phases. And I will start with discussing the paper with Emanuel and Maurizio that came out in March, where we in particular considered Landau-Ginzburg phases in this context. So I will start off with the hemisphere and also briefly recall what the worldsheet definition of a D-brane central charge is. So from the worldsheet perspective, the D-brane central charge is a disk amplitude. So you take a disk, you put a D-brane on the boundary of the disk, and then you stretch it into a cigar and you perform a topological twist. And then you insert an operator, either from the chiral or the antichiral ring, onto the tip of the cigar. And through the stretching and the twist, this state actually is projected onto the ground state. And the central charge is this bulk boundary two-point function. And a comment that will also be important a bit later is that in order to get the central charge, you have to put either an A-brane here and an element of the CC chiral ring at the tip, or you take a B-brane at the boundary and an element of the AC chiral ring over here. So what we will discuss in this talk is the latter case. We will have B-branes and AC operators. And for those who are familiar with the topological string, I just want to comment that in the topological string language, that would be considering B-branes in the A model. So it's actually something that's not really captured by the topological string. And that's also what makes this partition function so interesting. Okay, so this is the worldsheet picture. And yes, let me go on and recall this formula that you've already seen in the overview section of the talk. So I told you in principle what that is and how to compute it. So what we will do now is to look at the right-hand side and give more details about what's written here. So what I will focus on from now on is Landau-Ginzburg orbifold phases. So like the simplest non-geometric phases that you can find in a gauge linear sigma model. And the plan is to define the object on the right-hand side of this equation within the context of Landau-Ginzburg orbifold, and then show that the results match with the hemisphere partition function, and also with mathematical results where many of these objects are actually already defined. All right, so I will now go step by step and try to define what these properties are in a Landau-Ginzburg orbifold context. Good. Again, I will only introduce what I need to define the properties we have here. So to get to a Landau-Ginzburg orbifold, we have, much like in the gauge linear sigma model, a superpotential with some, depending on some chiral fields, xi. An orbifold group, so now G is a discrete group, and actually we will assume that it's a product of set D, so it will be a billion orbifolds in our context. We have a matter representation for the axis. And I also introduced the left and right moving U1R symmetry. Okay, so the first thing I have to discuss is the state space and the pairing that enters this formula. So in the CFT, we have all these chiral rings, CC, AC, and so on. And in the Landau-Ginzburg orbifold, they are realized in terms of twisted sectors, where these twisted sectors are labeled by elements of the orbifold group G. And I will choose certain basis elements. And actually by using this notation, I already have made a restriction that it's a technical restriction that you don't really need in the Landau-Ginzburg orbifolds, but you will need it to define all the other quantities that enter this formula I have stated. So I will now restrict to so-called narrow sectors, which are one-dimensional twisted sectors, and the only element in these twisted sectors or chiral rings is the identity operator or the vacuum. So this is what's essentially the definition of a narrow sector, and all the sectors which are not like that are referred to as broad. And the pairing we're going to use, or we're going to find in this formula, is a pairing on either you can define it either on the AC ring or the CC ring. You choose a basis elements of these narrow twisted sectors, and then this is the definition of the pairing. And I want to stress that this is not necessarily the pairing you would expect, because I had the worldsheet definition here where I said this two-point function is actually a pairing between something that's associated to the CC ring, namely a B-brane, and something associated to the AC ring inserted at the tip. So one would expect a pairing between the CC and the AC ring, but we don't really know how this works. But there is, of course, an isomorphism between these two rings through spectral flow. So we should understand when we want to use this pairing, there has to be some non-trivial spectral flow somewhere. And this is actually also what we observe in our work, and it's very consistent with the partition functions we compute. But in the end, we will use this pairing in this formula. All right. B-type D-branes in Landau-Ginzburg orbifold are actually easily explained because they're also matrix factorizations, and the data is more or less the same as what I had in the description of the B-branes in the gauge linear sigma model. So again, we have a Chern pattern space, we have a matrix factorization, and we have these two matrices representing now the orbifold group and the vector R symmetry on the boundary. And actually in 2004, Johannes Walcher told us how to compute the Chern characters of a B-brane or a matrix factorization in Landau-Ginzburg orbifolds, and it's given in terms of a residue formula. And I will not explain all the details about this formula, but you will see the matrix factorization enters, this orbifold representation enters, of course, a trace over this Chern pattern space enters, and we're inserting a bulk operator. So this is also a disk bulk boundary two-point function. We're inserting a bulk operator corresponding to a state in the gamma twisted sector. So this formula is more general than the restriction I've made previously to narrow sectors. So in the case that we will considering, actually this phi gamma here will be the identity operator. And I should also stress that the states and also these objects here naturally lives in the CC chiral ring. Okay, so for now, going back to this formula, what we know now is the state space we want to use. We know what the pairing is we want to use, and we have the Chern character. So what I haven't told you yet is what the gamma class and the I function look like. And in order to define this, it's actually not enough to sit directly at the Landau-Ginzburg point, but what you have to do instead is you have to turn on marginal deformations away from this Landau-Ginzburg point. And we take quite a lot of effort to encode the information about this deformation into a certain matrix that we call Q with rational entries. It's really quite a technical derivation from the Landau-Ginzburg perspective to derive this matrix Q. And I will refer you to the paper for details. The point, so just to say that N is the number of chiral fields and H is the number of marginal deformations, again, restricted to these narrow sectors. And having this matrix, we can then give a formula for the gamma class. So in this context, the gamma class is an endomorphism on the state space that acts diagonally. And these eigenvalues, say, associated to each of these narrow twisted sectors looks like this. So we have here this matrix Q entering that I just told you we derived. And in order to see the connection to the twisted sectors, that's actually not obvious. And we also take some time in the paper to see how this works. So I hope you take my word for it. So these are integers, positive integers. And you can actually associate each of these integers to a certain twisted sector. And there is some periodicity involved. And actually the definition of this angle bracket here tells you that these objects, the results you have here is also periodic. And in the end, you have one expression for each narrow twisted sector. So that's how we define the gamma class in this Landau-Ginzburg context. And then finally, we need the I function. So the I function it can be expanded in terms of this basis of the state space, again, restricted to these narrow sectors. And given this matrix Q that we compute, and furthermore, these QJs are the left R charges of the chiral fields, we find these expressions here. So what we have here, these U's, they are the local coordinates near the Landau-Ginzburg point corresponding to the deformation parameters. And then we have this quotient of gamma functions here, where again, integers enter that and making some clever coordinate transformations, we can then associate certain choice of these integers to the twisted sectors. but that's quite technical, so I will not go into details. So now this is all we have, but let me briefly mention a connection to the J function. So in principle, the formula I gave you for the hemisphere partition function, or the central charge in the Landau-Ginzburg orbifold case, included the I function, but actually in the paper we are writing the J function. So what is the connection? So the J function and the I function are related by a transformation to flat coordinates. And the flat coordinates, these are not the coordinates U that come in here, but coordinates that I will call T. This is a bit of an unfortunate choice because it's also not the Fi parameter of the GLSM. And these flat coordinates can be identified with the deformation parameters of the marginal deformations of the worldsheet CFT. And there's actually a prescription in the Landau-Ginzburg orbifold context on how to get the definition of these flat coordinates. So you choose some components of the I function that correspond to AC states with a certain left and right R charge, and another component which has R charge 0, 0. And then this quotient determines the flat coordinates. And the J function is then obtained as the quotients of the full I function by this component I0. And those who know mirror symmetry will recognize this definition of the flat coordinates actually as the mirror map, even though both the I and the J function should be interpreted as A model objects. All right. And so if you were to extract, for instance, Gromov-Witten invariance from these expressions, you would have to actually make this transformation to get the J function into the formula. Okay. So finally, to summarize what we did in the paper, these definitions of I functions and gamma class that I've shown you, we got them more or less exclusively from the Landau-Ginzburg data. And then we checked that these results are actually consistent with what is known from FGRW theory. So that gave an independent check of our results. And we also have some slight generalization of the FGRW results in the sense that we have models with more moduli and also more general gauge group. And as promised, the hemisphere partition function actually reproduces the results on the right-hand side of the equations when evaluated at the Landau-Ginzburg point. And the mechanism is that the GLSM gauge group is broken to the orbifold group. This matrix Q I introduced is related to the matrix of gauge charges of the GLSM fields. And the GLSM branes is just a map from matrix factorizations to different matrix factorizations. And we tested this in examples with up to 4 kilomoduli, including the computation of FGRW invariance that we did in this context. Okay, and in my remaining 6 minutes, I just want to give you a brief glimpse on some upcoming work with my student. So what we try to do is we try to do something similar for the sphere partition function. So here's the worldsheet definition of the sphere partition function. You take a sphere, or actually of the Kahler potential of MK, sorry. So you take the sphere, you stretch it, on one end you perform a topological twist, and on the other end you perform an anti-topological twist. You glue them together and you get a pairing, a topological anti-topological pairing that defines you the Kahler moduli, the Kahler potential on the Kahler moduli space. And these states 0 and 0 par are in physics term related by CPT conjugation. And what we did is we took a GLSM and looked at phases that are somewhat generic. So phases that are Landau-Ginzburg orbifolds fibered over some base manifold B. So this would be called a hybrid phase. And this includes special cases, Calabi-Yau complete intersections in toric ambient spaces, and also Landau-Ginzburg orbifolds. So all the cases we've covered for the hemisphere. And what we see is that the sphere partition function in any of these phases evaluates to an expression like this. So we have, again, some over twisted sectors coming from this orbifold. We have an integral over the base manifold. We have a sign with the grading operator acting on the state space. We have a quotient of the gamma class and its conjugate, where H here is a basis of H2 of the base manifold. And we have this norm of the I function squared. So this is the structure you get when you evaluate the sphere partition function in those phases. And we interpret this again as a pairing between the I function and its dual. And again, the pairing here would be the topological pairing, and our results indicate that these additional gamma quotients are sort of the analog of the spectral flow we saw in the hemisphere. So in other words, that there is some complex conjugation of the I function reproduces this quotient of gamma classes. Okay, yeah, what we did is, yeah, I already said, special cases are Landau-Ginzburg phases where the definition of I function, J function pairing gamma class is just what I've given you. In geometric phases, for Calabi-Yau complete intersection, we have the usual pairing on the even cohomology, and J function gamma class and so on you find actually for many examples in the literature. And yeah, as I said, our results suggest this way of complex conjugation of the I function, and this is actually consistent with observations that have already been done in previous papers, once for D-branes and also for leading order of the sphere partition function. Okay, and we did a lot of, or actually David did a lot of calculations for 14 well-studied one-parameter examples of toric complete intersections. So there's always a geometric phase, which is a complete intersection in toric ambient space, and another phase, because it's a one-parameter model, which is either Landau-Ginzburg or hybrid, or some even more exotic hybrids that Aspinwall and Pless are called pseudo-hybrids. And we observe this structure in all the phases, even these pseudo-hybrid ones, where it's a little more complicated, but also along the line of the formula I've given you. And actually, I should also note that even in certain hybrid models that are contained in these 14 examples, FGRW theory has been developed, and there are definitions of I function and gamma classes which match our results from the sphere partition function. And we also, for completeness, did a two-parameter model and got new conjectural results for I function and gamma classes in multi-parameter hybrid models. All right, and with that, So I hope you hear me again. I obviously just got muted. All right, so let me conclude. I'm almost done anyway. In these two papers, one still to come out, we conjectured universal expressions for the hemisphere and sphere partition function in phases of abelian gauge-linear sigma models. And we have collected a lot of evidence for these universal expressions for geometric Landau-Ginzburg and hybrid phases. Our results match with the mathematical results of FGRW theory, and also mirror symmetry were available. And we tested this for a lot of examples. And yeah, I guess this is only it's very example based and maybe only the tip of the iceberg. So I think there are quite a few open questions to look at, some more conceptual, some containing a lot of calculations. So for instance, we have this I function, the gamma class appearing, and it would be very interesting to understand better how, for instance, the gamma class, the significance of the gamma class in the worldsheet theory. And also here, I've only talked about abelian gauge-linear sigma models. So we're pretty confident that the results also generalize to the non-abelian case. I think an interesting conceptual question that currently is also a hot topic in mathematics is to lift this restriction to narrow sectors that we actually needed to define the I function, the gamma class. So there is some exciting new work ongoing in the mathematics community. I think with these techniques, we can actually say a lot more about these more generic regions in the moduli space and hybrids, in particular also in the context of D-branes, which has not been done yet. Also, we have looked at the sphere and the hemisphere, but there are a lot of other results of supersymmetric localization in 2D theory, which one can look at. Yeah, and in the end, finally, these formulas we've given are all conjectural, of course, and it would be very interesting to see mathematical proofs about that. And I think with that, my time is over now, and I thank you very much for your attention and the opportunity to present this work.
Thank you, Johanna, for this nice talk and being on time. Are there questions? I do not see. we should thank you.
Finally, yeah. The thing that is most troublesome was looking at.
And
okay.
and now I have to mute you all, correct?
Headache because
I just did it.
So I unmuted myself.
Great.
Now I unmute myself too. And are there any questions? Yes, there is a question from Ed Witten. Ed, could you please ask? You are muted. Hello, Ed. Can you please unmute yourself?
I can, until a second ago.
Sorry.
No,
Yeah, please go ahead.
I just was wondering if you could tell us what kind of mathematical results are there for you to compare to in the hybrid phases? Are there hybrid
Yes.
or
So
W
the
results?
results I'm aware of, I think the main result is, where is it? Sorry. Yeah. I think the main result I'm aware of is the PhD thesis of Emily Clader, who's a student of Rans.
Yeah.
She defined the gamma class and the I function and the J function for the hybrid phase of the bicubic in P5 and for the 4 quadrics in P7. So for the hybrid phases associated with these geometric calabi-Yau, the results are known and we reproduce them.
I see.
And there's also some interesting work by Xiao, I think, on German characters and D-branes in these hybrid phases.
I see. Thank you.
Okay, I don't see any other hands raised. Any other questions or comments?
Really?
There is one.
Yes, please, Ed, go ahead.
No, Cyril Clauset, I see his hands is up. There is another one up.
Oh, now, yeah, it showed. Apologies. Thank you. You're doing my job. Yes, Cyril, could you please, unmute yourself and ask a question? Please unmute yourself, Cyril.
Okay. Yeah, no, it works. Thanks. Thank you, Joanna, for nice talk. Can you say more about what's the difficulty with the broad sectors, especially from the localization, from looking at the formula explicitly?
Yeah, I can maybe say a little bit about what the difficulties for the broad sectors is in the GLSM. So from the GLSM perspective, it's very hard to see those moduli. For instance, if you are in a toric setting, these moduli would be moduli that are not inherited from the ambient space. So it's actually not, from the GLSM point of view, it's not very clear how to describe those. In the Landau-Ginzburg language, the broad sectors would correspond to those twisted sectors which do not just contain the vacuum state, but also further states which you can characterize by monomials. And as far as I understand, there is the mathematical formalism of FGRW theory has not been developed for these broad sectors, but there is some interesting recent work by Favero and Kim where they where they discuss the mathematical formulation of the GLSM, also including broad sectors. But I have to say I haven't really digested this yet. Does this help you?
Johanna? Hello?
Hello, yes.
Yes, Cyril is asking if that helped you.
Okay, yeah, he says, thank you. Okay. I see it in the chat.
Okay. Any further? I don't see any other hands raised. Anyone else? If not, we should thank Johanna again for this very nice presentation.
Yes, we checked it. It was correct.
Thank you for coming.
The actual proof or any,
Thank you.
understanding that this was the right answer or why integrams organized so nicely
And
was really far from us.
I'm muting you all. And this would conclude the first slot for the first talk. We should reconvene in about 15 minutes or less. And Dupay would be the next speaker. So see you in 10 plus minutes.
Hi, Du. Can you hear me?
Hi.
Hi. I've made you co-host.
Yeah, thanks. I will try to share my screen. Does it look all right?
Yes, it looks good to me.
Okay, fantastic.
Yeah. Jeff, I don't know if Jeff is there, but there seems to be still some confusion for me. Do you unmute or do I unmute and then mute people?
You mute and unmute.
Yeah, because there is, I was doing this, I guess,
Okay.
right?
Yeah.
Sorry about that.
You have all the power.
Anyway, okay, good. Thanks.
Great. So we start again in 10 minutes, yeah?
Yeah, we still have some time. Okay.
Okay, good.
So take a break and you should get ready. Okay, so there are a few more minutes before 9. Yeah, East Coast time. I have to go right. So I guess the time has come to start the second talk of the session. So the speaker is Pei from Harvard University, and we see the title on compactifications of 6D relative theories. Please go ahead.
Thank you. Before I start, I would like to thank all the organizers for putting together this wonderful event and for the invitation to speak. It's a great pleasure to be part of this. So I'll be talking about 6D theories and their compactifications. So let me start by telling you a little bit about why one would be interested in 6D theories and what one hopes to achieve by studying their compactifications. So for physicists, this class of theories are very interesting because they have unique physical properties and also because they play a special role in string theory and M theory. On the other hand, for mathematicians, this class of theory are interesting because they are usually very good at uncovering hidden connections between different subjects in mathematics. For example, taking some geometry and topological input, they sometimes can provide for you some hidden algebraic structures, hidden combinatorial structures, or some new geometric objects that looks very different from the geometry and topological data that you started with. In this way, it can serve as a bridge connecting different branches of mathematics. The way that it actually does this is through a process known as compactification. So I will say a couple of words about compactification. So if you have a quantum field theory in higher dimension, let's say 6 dimensions, then you can wrap that on a d-dimensional manifold. So here, MD will be my d-dimensional manifold, possibly with non-trivial topology. And then I can try to reduce the size of this d-dimensional manifold. Then effectively, I will have a quantum field theory in 6 minus d dimensions. The interesting geometric or topological information about the d-dimensional manifold will now be translated into interesting mathematical structures or interesting dynamical structure in the quantum field theory. This way, such theories in higher dimensions can provide a bridge between geometry, topology, and other kind of interesting mathematics. So let me give you a very incomplete and very quick summary of some applications of 6D theory in math. Usually, to have interesting applications, superconformal symmetry will be very convenient to have. There are two special classes of theories in 6D that have superconformal symmetry. One class is known as 6D 2,0 theories, and they are classified by ADE Dinkin diagrams. And they have already had numerous applications in math. For example, they can be compactified on 4 manifolds. And the 2-dimensional theory obtained, known as T of M4, turns out to know a lot about the model space of instantons. Studying them can shed some new light on the pioneering work of Nakajima and Waffle-Witten. And this class of theory also provide correspondence between vertex operator algebras and the study of topology of 4 manifolds. So on Monday, Thomas has already mentioned a little bit this correspondence. We can also consider compactifying this theory on 3 manifolds. The theory T of M3 can be used to define new invariants for 3 manifolds or to categorify old invariants. And in the talk by Pavel and Francesca, you have already learned about a new invariant Z hat and the interesting properties they have. And one can also compactify the theory on a 2 manifold. The topology of 2 manifolds is not as interesting as that of 4 manifold or 3 manifolds, but nonetheless, you'll get very interesting physical theories, and there will be very interesting mathematics. For example, by studying such theory, you will have a better understanding of the hyperkähler geometry of model spaces. And this theory also provides an interesting playground to study curious mathematical phenomena like wall crossing. And there is another connection to VOAs, as was nicely summarized in the talk by Thomas and Tomoyuki. And after further compactification, such theory also had applications in the geometric long length program. And there is another class of theory which actually contain the previous class. And these are 61,0 theories, and they form a much bigger universe. So many such theories are labeled by singular elliptic Calabi-Yau threefolds, which are much richer than just ADE Dinkin diagrams. And one may wonder whether they also have interesting mathematical applications. Just like their 2 0 cousins, they can be compactified on 4 manifolds. And it seems that these theories in 2 dimensions, T of M4, obtained in this way, encode some new invariants of 4 manifolds that are valued in the ring of topological modular forms. One can then consider compactifying this theory on 3 manifolds. And in some examples, one observes that T of M3 obtained in this way seem to give you certain modules over the ring of topological modular forms. And one can also compactify the theory on 2 manifolds. So there has been many interesting physics developments in studying such system. And I have no doubt that very quickly they will have very interesting math applications. So the talk today will not about any of these applications specifically, but it will concern all of this because today I'm going to focus on some universal aspects of compactification of these 6D theories. the tool that we're going to use will be symmetries and their anomalies. And this is based on joint work with two amazing collaborators, Sergei Gukov and Bo Shenxin. So this is still ongoing work, so any comments and suggestions are extremely welcome. So let me first give you a quick reminder for quantum field theory with anomaly. So if a quantum field theory has symmetry, global symmetries, and they have anomaly, the quantum field theory can still be consistent, but it should be more naturally viewed as living on the boundary of a topological theory which lives in one dimension higher. For the usual 2-fold anomaly that we're most familiar with, the topological theory in the bulk is invertible, meaning that its Hilbert space on any d-dimensional manifolds is one-dimensional. In this case, one will say that the boundary QFT is either absolute or projective. There is a distinction between these, but in this talk, I will not distinguish between actually absolute theory versus projective theory. What I will distinguish is this situation and the situation when the TQFT is non-invertible, meaning that in some cases, the Hilbert space on some D manifolds can have larger dimension. And in this case, we will say that the boundary quantum field theory is relative. For relative quantum field theory, one cannot just define its partition function. Instead, one has to first specify a state in the TQFT Hilbert space. If one has further a set of bases for the TQFT Hilbert space, then one can define a collection of partition functions and assemble them into a partition vector of the boundary theory. So one interesting fact about 6D theories is that most theories that we know in 6 dimensions are actually relative. For example, for the 2.0 superconformal theories, they are classified by ADE Lincoln diagrams, and all of them are relative except for the one labeled by E8. And the bulk theory, the topological theory living in 7 dimensions, is described by a 3-form Chern-Simons theory. This is what the action looks like. It pretty much looks like the Chern-Simons action in 3 dimensions, but instead of having a 1-form connection, now the dynamic field is a 3-form U1 gauge field. But the levels are still going to be quantized, and they can be assembled into a coupling matrix. In the case when we are considering 6D 2.0 theories, this coupling matrix will be identified with the Cartan matrix of the corresponding Lie algebra of type ADE. One can further define an abelian group in this way. It is often referred to as a defect group. Physically, elements in the defect groups labels 3-dimensional defects in the 7D TQFT. And these defects is very like Wilson lines in 3D Chern-Simons theory, in that they have braidings and spins. One way to encode the data for braiding algebraically is to consider the symmetric pairing on D. This is sometimes referred to as a Dirac pairing from the boundary perspective. And the spin for these defects can be viewed as a quadratic refinement of this symplectic pairing. So I will denote as Q. Now, given a 6 manifold, by combining the pairing on D with the pairing in cohomology, we can get an antisymmetric pairing in H3 of the 6 manifold. And in the study of quantization of the TQFT on the 6 manifold, it's very convenient to consider the notion of a polarization defined as the choice of a maximal isotropic subgroup. And it is expected that given such a subgroup, denoted as lambda, one can obtain a state in the TQFT Hilbert space, which specify a particular partition function for the coupled system. So our goal today will be to first look at this slightly more carefully and refining it a little bit, and then generalize this to the problem of compactification a manifold with dimension d less than 6. So before doing that, we'll take a slightly different perspective on polarizations. Instead of defining it using group theory, we'll define it using physics as the possible ways to obtain absolute zero-dimensional theory by compactifying on a 6 manifold. And here there is a small caveat. We only consider compactifications that are universal, meaning that this is compactification that can be done for any boundary theory, provided that they are coupled to the same bulk theory. So this is a cartoon of a naive dimensional reduction on 6 manifold. In 60 and 70, the 60 boundary theory has two-form symmetry. But this two-form symmetry has anomaly, and that anomaly is captured by the 7-dimensional transamination theory. After compactification, when we have a 0-dimensional theory on the boundary, you will now have an anomalous -1 form symmetry. And there will be a 1-dimensional TQFT that describes this anomaly. Operators in the TQFT come from wrapping the 3-dimensional defects in the 7D theory on 3 cycles. So here, alpha, beta start their life as 3 cycles, and after compactification, they become operators acting on the Hilbert space associated with the 6 manifold. And in general, they won't commute. The phase that describes their failure to commute is proportional to the pairing between alpha and beta. So one way to get absolute theory in this setup is to gauge part of the -1 form symmetry on the boundary. Since this symmetry is anomalous, one cannot gauge all of it. One have to gauge a subgroup. And to be consistent, this subgroup has to be anomaly-free. And that's the same as being isotropic. And further, if you want to get an absolute theory, the bulk TQFT has to become invertible after gauging. And that's the same as the maximal condition on the subgroup. So from the bulk perspective, gauging such a subgroup on the boundary is the same as acting by the projection operator defined in this way on the boundary. And it will be well defined because lambda is anomaly-free, and it will project onto 1-dimensional subspaces because lambda is also maximal. Further, one can define a collection of projection operators with background field B. B will be valued in the dual of lambda. And one can check that they are indeed projections onto different 1-dimensional subspaces with no overlap. Therefore, this collection of projection operators give you a decomposition of the Hilbert space. But that's not the same as choosing a basis yet, because choosing a basis would require choosing faces in each 1-dimensional spaces. And in general, there can be some phase ambiguities, and there can be obstructions of choosing canonically the phases. One can only choose canonically the phases if the do group lambda check is also anomaly free. And that's the same as saying that this short exact sequence split, which is the same as saying that H3 can be decomposed into lambda plus a lambda bar. Lambda bar will be isomorphic to lambda check, and it can be viewed as a lift of lambda check into H3. And the basis will actually depend on this particular lift. And then we'll have well-defined basis in the Hilbert space, which can now be identified with the C-span of lambda bar. We will use this notation for the basis vectors that are labeled by B. And each of them give you a component in the partition vector. So for another polarization, the partition function will be a linear combination of this basis of the these building blocks. And one can get a formula like this by acting the projection operator on a particular basis vector. But actually, there is an ambiguity in defining this projection operator. And that's the same kind of ambiguity in ordering operators that puzzles founding fathers of quantum mechanics about 100 years ago. So if you upgrade alpha to an operator alpha hat and beta to beta hat, so what happens to alpha plus beta? Well, you can send that to alpha hat times beta hat, but that's different from beta hat times alpha hat. What you really want to do is to send it to alpha hat times beta hat times square root of the phase that appear in this commutation relation. So to do this consistently, we need to choose a quadratic refinement. This will be given by a quadratic function Q on lambda prime, and it will have some compatibility property with C pairing. And the partition function will actually depend on Q, because now the projection operator will depend on Q. And it will be simply a linear combination of the building blocks like this. So to give a quick example, consider the 6 manifolds being S3 times S3, and D being Z2. Then H3 will be a product of 2 Z2s. We will refer to the first Z2 as electric and the second Z2 as magnetic. The Hilbert space will be 2-dimensional, and it will be spanned by the 2 vectors if we have chosen electric basis. And there are going to be 3 maximal isotropic subgroups. You can take the first Z2, second Z2, or the diagonal Z2. They are all maximal isotropic. And anticipating connection with 4-dimensional physics, we will refer to these 3 choices as SU2, SO3 plus, and SO3 minus. But each of them has 2 quadratic refinements. So in total, there are going to be 6 polarizations. And they correspond to these 6 different vectors in the Hilbert space. And they can be maybe referred to as the SU2 theory for the 0, spin SU2 theory for 1, and SO3 theory with a Z4 valued discrete theta angle for the remaining 4. Since we have 6 different vectors in a 2-dimensional Hilbert space, any 3 of them will have a linear relation. So you will have relation between partition functions like SU2 equals to SO3 plus, well, SO30 plus SO32. And you have many other relations. These are relations that is very similar to what you have seen in Eric Sharp's talk on Monday. And these relations are universal in the sense that it comes from the bulk TQFT and will be valid for any boundary theory that can couple to the bulk TQFT. Another interesting feature of this is that there will be an SL2Z action acting on H3. So it will act on these maximal isotropic subgroups, and it will act on these 6 different states and the 6 different polarizations. And you can easily work that out, and you end up this diagram. And after lifting this to 4 dimensions, this will agree with a conjecture in the literature found when they study different versions of SU2 theory on non-spin manifolds. And this relation is also universal. The action of the mapping class group will be exactly the same if the bulk theory are the same. For example, E7 would couple to the same bulk theory, and you have the following action of mapping class group for the E7 theory. To give another example, consider again 6 manifold being product of 2 3 spheres, and D being now product of 2 Z2s, and the pairing is between the 2 Z2s. This would be relevant if you want to study the compactification of the 62,0 theory labeled by spin 8. Now there will be 15 maximal isotropic subgroups, and each of them will have 4 quadratic refinements. So in total, you will have 60 different polarizations. The Hilbert space will be 4-dimensional in this case, spanned by these 4 vectors, and they correspond to different versions of spin 8 theories. And similarly, there will be 4 different versions of SO8 minus theories, given by these 4 different vectors. And again, one can study mapping class group action. There will be 7 orbits for maximum isotropic subgroups, and there will be 16 orbits for polarization after the quadratic refinement. So one example.
Sorry to interrupt you two, but Edward Witten has his hand up. Ed,
Yeah.
if it's not too late, would you unmute yourself and ask the question? Yes, can you unmute yourself, please? So I have just noticed that, but his hand is probably was not.
Only now I could unmute myself. Until a second ago, I couldn't. I just wanted to, first of all, I hadn't intended to interrupt your lecture. I'm sorry. I thought I'd ask at the end.
No problem.
But I wanted to understand intrinsically what you're constructing. And I thought what you're constructing might be absolute theories in 3 dimensions that can come by compactifying this relative theory in a single S3. Because we called it S3 times S3, it could have been anything times S3 and would have led to a similar discussion.
So,
in 6 dimensions, I don't quite know what you're discussing, but I thought maybe you're discussing relative theories, sorry, absolute theories in 3 dimensions.
So here we are constructing absolute theory in 0 dimensions. Later we'll do the same, but constructing absolute theory in higher dimensions. In this talk, I actually won't be talking about 3 dimensions, but I will talk about 5 dimension, 4 dimension, and they will share a lot of similarity with the this case in 0 dimensions.
Oh, you said, I see.
So polarization on S3 times S3 will provide for you absolute theory in 0 dimension. And in some cases, it might actually come from an absolute theory in higher dimension. But in this case, I'm not absolutely sure whether they can come from absolute theory in 3 dimension. Shall I continue? We can have a longer discussion about it later.
Sorry for this interrupt, but I think it was useful. And then you can continue discussion after your talk. Maybe, yeah. Could you please continue? Sorry.
Yeah. Okay. So one particular orbit without refinement is given by the following, and this agrees with how the corresponding 4D theory transform. But these 4D theories are theories defined on spin manifolds. And over this orbit, there will be a 4-fold covering by 2 orbits that looks like this. This is what one gets after the refinement. And each choice of maximal isotropic subgroups is now covered by 4 different polarizations, which differ in their quadratic refinements. And again, this action of mapping class group is universal. So you will find exactly the same action in the case of spin 8n. So one thing that is special about spin 8 is that it has triality. For spin 8n, naively, it should not have triality, but all the orbit is compatible with triality because they simply couple to the same bulk theory. So now we will study compactifications on D-dimensional manifolds with D less or equal than, let's say, less than 6. And we want to generalize slightly the notion of polarization to a notion of polarization on a D manifold. Before, we have defined the set of polarization as ways of compactifying to get absolute 0-dimensional theories. Now we simply generalize that to ways of defining of compactifying theory to get absolute 6 minus D-dimensional theories on a D manifold. And again, we only consider reductions that are universal. These are reductions that make sense for any boundary theory coupled to the same bulk theory. Notice that compactification of absolute theories is unique. So one will have a map from polarizations on D manifolds to polarization on D manifolds times another manifold. So using this, you can view a polarization on D manifold as a family of polarizations on manifolds of the type MD times M6 minus D. So there will be a family of usual polarizations. And this family is supposed to be functorial in the M6 minus D direction. I will comment on what that exactly means later. So a difference between higher dimensions and 0 dimensions is that now you will have 2 different types of polarizations. The first type is what I will refer to as pure polarizations. And they are obtained by choosing a subgroup of the cohomology group of MD with D coefficient. And they are required to be trivial under the pairing. And it can be decomposed into different graded pieces. And using this, the maximal isotropic subgroup, lambda M6 minus D, will be given by the image of this map in cohomology. But actually, there will be other possibilities, and there will be mixed polarizations. So to see this more concretely, let's look at the example. Let's consider polarizations on a circle. And we will take D to be ZP, with P being a prime, to slightly simplify the problem. So given a 5 manifolds, any polarization on S1 would specify for you a maximal isotropic subgroup inside this cohomology, which can be identified with H2 plus H3 of the 5 manifold. And it turns out that there will be 2 pure polarizations. One corresponds to the choice that L equals to H0 of the circle. For this choice, this isotropic subgroup will be H3 of M5. And it can be perhaps referred to as the SUP theory, because this is literally what you get if you reduce the 2,0 theory of type AP-1. There's another choice of pure polarization given by H1 of the circle. This corresponds to this choice of the of a maximal isotropic subgroup inside H3 of the product. And this is perhaps can be referred to as the PSUP theory. But actually, there are going to be mixed ones, and they are constructed using the following. So you take any elements inside H2 and look at its image under the Boxer homomorphism to H3. And you multiply that by K. So this defines for you an element in this sum, and you consider all such elements. This also turns out to form a maximal isotropic subgroup. And for K that is not equal to 0, it's not given by any L. So this will be an example of a mixed polarization. And these theories physically can be related to PSUP theories, but with a discrete theta angle. So before pursuing more examples, we will make some general comments about symmetry and spectrum. So for pure polarizations, the degree D minus n piece of L will label charges of operators of dimension 2 minus n. So in the 2D example, for L being H0, L can be viewed as possible charges of the Wilson line in the SUP theory. For the other choice, L will be H1, and these label charges of the magnetic string in PSUP theory. But how about mixed polarizations? What symmetry do they have? And what's the spectrum of operators? The spectrum for mixed polarization, or in fact, for any polarization, can be studied by defining a spectrum group. So it's a subgroup of the cohomology of MD. And it's defined as a union of the image of lambda M6 minus D under the following map in cohomology. So I won't say more about the construction, but I will remark that you get back L for the pure polarizations. So it's a good measure for the spectrum of operators, at least in the case of pure polarizations. But if you're considering mixed polarizations, you actually get a spectrum group that looks like it's improperly quantized. In other words, this pairing will be non-trivial as P. And physically, this would indicate that this theory seems to contain operators that does not satisfy Dirac quantization condition. So how can this theory be consistent? It turns out that the theories are consistent because some of the theories does not exist independently. They only exist on boundary of some other theories. And this can be interpreted as the Witten effect or generalization of the Witten effect in the presence of discrete theta angle. In the 5D theory example, on the boundary of the magnetic string, you will have something that has fractional charge under the one-form symmetry. So it can be a fractional Wilson line, for example. And the fraction Wilson line will not be properly quantized, but that's completely fine. So to get the correct symmetry for the theory, we need to consider a subgroup of independent objects, and the symmetry will be the dual of this. So for example, in the PSUN theory, with discrete theta angle, you will have two-form magnetic symmetry, but not one-form electric symmetry. So we have defined the notion of polarization, but how to actually classify them? For pure polarizations, one can proceed by looking for all such subgroups that is trivial under the pairing, similar to what you would do when you study polarization on a 6-manifold. But how about these mixed polarizations? It turns out that they can be classified by relating them to SPD faces, which are the same as invertible TQFTs with symmetries, but in 6 - d dimensions. So how can this be done? The way to see this is to consider this relation between partition functions. Now I've added in the dependence on the 6 - d dimensional manifold. So now the phase is not just a function of alpha. Now it's also a function of the 6 - d dimensional manifold. But you want functoriality, because actually this will be certain amplitude in the 7D TQFT. So that would imply that this phase itself is a partition function of an invertible TQFT with symmetry. And this can be classified and by relating them to cobordism groups. If the theory corresponding to a polarization lambda is given by a Lagrange description, let's say a gauge theory, then very often this invertible TQFT has an interpretation of a discrete theta angle. So now let's look at compactifications on 2 manifolds. Example 1, you can consider 2 torus. And first, you look at pure polarizations. They are given by choices of 2 subgroups of the cohomology of T2. One is an isotropic subgroup inside H1 of T2. Another is a subgroup inside H0 plus H2. We actually have already encountered this group because it's exactly H3 of S3 times S3. And that's why I was using 4D notation 10 minutes ago when I was discussing zero-dimensional physics. It will be literally just the same in 4 dimensions. So all this SL2D transformation apply to the 4-dimensional theory. For the second part, it will be the same actually as the cohomology of S1. So that's also something familiar and something that we have seen before. So for 62,0 theories, if you compactify on T2, you will get a 4D gauge theory with a matter. To keep track of all the symmetries, it's a good idea to make sure that one of the scalar is actually compact. Then the choice of the first subgroup L1 will tell you what is the global form of the gauge group and what is the discrete theta angle. And the second choice of L0 will tell you what is the global form of this compact scalar. It can be a group that is different from G. And depending on the form of G0, the theory can have 0-form symmetry and 2-form symmetry given by the center of G0 and pi1 of G0. And they can also sometimes have mixed anomaly. An example of a theory that one can get by compactifying is a SO3 minor theory with SU2 value scalar, for example. And these are the pure polarizations. But there are many mixed polarizations. And there will be charged objects in dimension 0, 1, and 2. And on the boundary of the two-dimensional objects, which I call axion strings, there will be fractional Wilson and Tooth lines. And on the boundary of Wilson and Tooth lines, you will carry fractional charge under this symmetry. This is a general feature for theory obtained from these mixed polarizations. One can also consider a genus G Riemann surface. And the problem will be almost identical, except that L1 is not an isotropic subgroup inside H1. This problem was considered in a paper by Tachikawa a few years ago, with the choice that L0 is the degree 0 piece. But there are, again, going to be many mixed polarizations. And they differ from the standard one by some choices of discrete theta angles. And this would give you some new class S theories. So if you are amazed by the interesting connection between class S theory and mathematics, you should try generalizing all of this to these new class S theories. So I think I'm running out of time. So I only have a few quick comments, but maybe let me just show all of this. So 2 comments is about compactification in 3 and 4 dimensions. The third comment is about isometry of MD. I didn't discuss this, only discuss mapping class group action, but they're also interesting and they act in a very non-trivial way. Sometimes they act in a way that it combines with other symmetry to form a higher group symmetry. Even for compactification on S1, you can have actually an anomalous 3-group symmetry. Oh, there are many more comments, but since I'm over time, so thank you.
Thank you, Du, for this nice talk. I'll now unmute everybody. So are there any questions? Yes, I see Nicola Dedushenko has a question. Yes, please, go ahead.
I do.
Nicola.
Nice talk.
Thanks.
So I actually have a few questions. The first one, I feel like you actually intentionally designed it to provoke a question, so I'm asking this. What is the -1 form symmetry?
Oh, yeah. So -1 form symmetry is not like any other symmetries. So,
excuse me, not to interrupt you, but I have to mute you all, and then you two guys have to unmute yourself. Sorry for that. So, Mikola, I see you are unmuted. Yeah, and so.
Okay, I think I'm also now muted.
Sorry for this.
So, -1 form symmetries has symmetry defects being space filling. So they are transformation on the theory. So if you have discrete theta angle, acting by a -1 form symmetry can change that discrete theta angle.
Mm-hmm.
So in this particular 0-dimensional example, there will be indeed some discrete theta angles. And then you can shift this discrete theta angle by acting by -1 form symmetry.
I see. So there are no charged objects. It's just an operation on the theory.
Yeah, exactly. So that's why I put this in quotes.
Mm-hmm. Another question, but I think you already kind of answered, because at the beginning you were talking about mapping class group, and I was wondering what is of what, but then it's probably T2, right? It doesn't have any interpretation in terms of S3 times S3.
Well, for the case of S3 times S3, the mapping class group of S3 times S3 still acts. And actually, the mapping class group of S3 times S3 can be quite complicated because of exotic phenomena. But the action on homology will factor through the quotients to SL to Z. So it will actually be the action of mapping class group of S3 times S3. But
is it clear?
Captured.
Is it clear what's T? Like S is probably exchanges the two S3s.
Well, it will be the same. You can still do exactly the same as the 2-dimensional torus. So the pi 3 of S3 is still Z, just like pi 1 of S1.
Okay. And final question. So just to understand, so what part of this is known, what part of this is new? Do I understand that correctly, that the main result is about computing polarizations and products of manifolds and identifying the physics interpretation?
Yeah, exactly. Mm-hmm.
Okay.
All right, thanks.
Oh, thank you, Mikola. And the next question is by Kumrun Bafa. Kumrun?
Hi, Kumran.
Hi, nice talk. I have a question. The 61,0 theories, there are also the little strings that are interesting. And in those cases, you get matrix Kij that you had, which are have null directions. Does that introduce an interesting story for you for polarizations in that context?
So in that case, there will be a degenerate direction in K, is that correct?
Yes.
Then the theory will not be completely topological. You will have some propagate degree of freedom. So one probably need to take into account of that. Provided that somehow one can remove this, then the same story can still apply. But with this massive degree of freedom, then one need to maybe find a different way of treating them.
And also, when you say topological, so you were studying in the first part, you were specifically keeping some supersymmetry, but in the more general setup you were describing, supersymmetry did not play any role. So you were talking about the more general topological aspects, if I understood correctly.
Yeah, exactly. Mm-hmm.
Are there any specific aspects of preserving supersymmetry that enhances the structure you're talking about, or just orthogonal to the questions we were talking about?
Sometimes there can be enhancement. So for specific theory, usually there are more things that one can do in the compactification, and symmetry can also be enhanced. But so far we have been focusing mostly on these universal aspects. As long as the boundary theory can be coupled to the same bulk theory, it does not matter too much whether it's supersymmetric or non-supersymmetric, or having 1-0 versus 2-0 supersymmetry.
Yes. Okay, thank you.
Okay.
Thanks.
Well, thank you, Kumrun. The next person is Arnav. Can you please unmute yourself? Yes, go ahead.
Yeah, hi, can you hear me? Tell me if there's an issue with my mic.
I can hear you.
Okay, cool. Could you just give me an example of what the Hitchin system looks like for one of your more exotic class S theories, like the Coulomb branch of the moduli space in R3 process 1 for one of your mixed polarizations? What happens to the Jacobian of the spectral curve type description?
Yeah, okay. So there are, one can ask this question at different level. So first of all, there are pure polarizations on sigma times T2 that are still kind of exotic. So there are some standard ones giving rise to SU, for example, SU2 Hitchin moduli space. And there's another one giving to SO3 moduli space. And then SU2 moduli space will have different quotients. And many of these pure polarization will be a different quotient of this. And to keep track actually of all the symmetry, it's a good idea maybe to consider a multiplicative version of Hitchin system. And then one can often relate all these pure polarizations by gauging. And from the target point of view, this is basically doing quotient or covering. So, but there's also mixed polarizations. I don't completely understand the geometry of the moduli space in that case. So I think it would be a very interesting question to ask. So the mixed polarizations, of course, at level partition function, you'll be linear combination of those of pure polarizations. But the geometric objects or algebraic objects associated to them can be quite different.
Oh, is it still going to be like essentially the same geometry, but just quotiented in a slightly different way? Or do you think it really might be twisted up, genuinely some different vibration stuff?
I think they should not be simply be just quotients. There can be more structures.
Okay. Oh, thank you.
Thank you, Arnav. The next speaker is Pavel Putrov. Pavel?
Hi, Pavel.
Yeah, go ahead.
I have a bit of technical question. So you say that you need to to define a physical system. You need to fix quadratic refinement of
yeah, exactly.
form on a D. But do you consider certain equivalence, some equivalence relations on the quadratic refinements?
So I have already defined it in a way that they are all equivalent. So they are labeled by like two torsion elements in the dual of lambda prime. And you can see that each of them are actually equivalent. But there's a way to do this in 7D physics by introducing some background field. In that language, there will be a lot of redundancy. But what I described will be like the thin quotient by all the redundancy. Okay. So by definition, for two different quadratic functions, they will give you different states in the Hilbert space. So we'll give you different partition functions.
But for example, like if I want to compare with kind of Spincher-Simons theory in 3D, I think you also have to specify, you have to pick a quadratic refinement of this co-kernel of the lower matrix, but you also, this quadratic refinement should satisfy under Gauss law constraint. And
right.
Gauss sum constraint.
Yeah, exactly. So so what I described here are actually theories that are not like spin transamination theories. So in that case, you need to find some Z2 extension of D. And then indeed, there will be a more interesting story. So I think for 2,0 theory, this is good enough. For 1,0 theory, indeed, one might in general consider along the line that you suggested.
Okay, thanks.
Okay, thank you, Pavel. Now, Ed Witten, please.
Could you explain again the distinction between pure and mixed polarizations? Say when you're compactifying on a 2 torus? It's not the case that one gives a relative theory and one gives an absolute theory in the lower dimension, I assume.
They all give absolute theories.
Okay.
So I think it's perhaps simplest to do this in 5D. It's of course also possible in 4D. Many 4D ones are actually just dimensional reduction of these 5D absolute theories.
Right.
So here, the two pure ones is given by SUP theory and PSUP theory.
Yes.
Okay, so but you can introduce discrete theta angle term.
Yes.
In the PSUP theory. If you have a W2 for the gauge bundle, you consider W2 times boson of W2 with a coefficient. That's an absolute theory, and this discrete theta angle have Witten effects to introduce some fractional charges on the boundary of other objects.
So okay, what's the principled reason to call one pure and one mixed?
So pure ones come from a subgroup of the cohomology of SD.
I see.
And geometrically, they correspond to, so choosing a T-type state corresponds to choosing some 7 manifolds. And they're particular nice type of 7 manifolds, such that you just need to choose.
You choose a 3 manifold whose boundary is the torus. Or
yeah, exactly.
Or something.
Yeah. In this case, a disk with a boundary being S1. But
well,
yeah, but the mixed ones are going to be more complicated 7 manifolds.
Okay, but okay, what you've listed on this page are all the presumably meant to be all the Lagrangian subspaces of the middle dimensional cohomology of M5 times a circle that you can describe universally.
Yeah, yeah, I believe this out.
What's a precise form? Is there a precise formulation of that statement? Or are these just, I mean, I can see that these are the ones we can think of, although the mixed ones are harder to think of.
So the mixed ones can still be classified using SPD phases. And in this dimension, the only SPD phases that we can think of are just of this type, given by W2 prime delta W2 prime. That is relevant. So I believe that in this dimension, using the connection with cobordism group, one can completely classify these SPD phases. Then one can argue that these are the only mixed ones.
SPD phases of what, by the way? Okay, I think I'm asking too many questions though, and we're running out of time. So maybe I should talk to you privately.
Right, maybe you can continue that privately or in a
So
breakout.
to say just very quickly, so these SPD phases are these coefficients that appear in this decomposition. And they have some interpretation as some amplitude in the 7D TQFT. And because of that, they are actually behaving like TQFT in 6 minus D dimensions. And if this can be written down concretely as a function of B alpha, then it will just look like a discrete angle term in the theory that deform the theory.
Okay, thanks.
Yeah, okay.
Thank you.
Due to the fact that we are approaching the full hour, there is one more question by Ali Sheffer. If it can be short and sweet, please, Ali.
All right, so I'll be very quick. What does it physically mean to make a choice of a quadratic refinement? And sometimes you were making that choice, sometimes you weren't. Is that?
So in general, we always want to make the choice. So in 0 dimension, we always want to make the choice. The problem in high dimension is that you want a choice that is compatible with functoriality. So you actually, so here the phases actually take into account of the quadratic refinement.
And what does it physically mean to make a choice like this?
Yeah, so in this reduction, there are background fields. And you should take the point of view that all background fields are more or less equal. So you need to consider all of them. So these are background fields that Z2 valued and coupled to C in the term like C dx. And they have the property that they will not change braiding, but it will change the spin of defects. So you need to ideally consider all of this. But you, on a general manifold, you want to consider those that are behaving nicely in the TQFT fashion. So, but you actually see some of this here. So let's remember that the SO3 plus theory and SO3 minus theory are distinguished by a discrete angle that's written down using Pontryagin square.
Yeah.
And that's exactly quadratic refinement. So quadratic refinement in lower dimension is like square divided by 2. But in higher dimension, it's a cohomological operation like Pontryagin square.
All right, thank you.
Okay, thank you. Let me unmute you all and let's thank Du again for this excellent talk.
Thank you very much.
Now we will continue with the last speaker of the first session on Wednesday, and this is Jonathan Mboya-Ezole. So I guess I need Nathan's help, and Mboya, can you please set up your slides?
And I'll give a regular Blackboard talk.
Oh, okay. All right. So maybe I should just announce, right? Mboya is from Northeastern University, and he'll talk about meta representation and the geography of Lie subalgebras, an extension of Katz-Waffa method. Okay, Jonathan Mboya, please go ahead.
Hi, everybody. So it's a pleasure to talk at String Math. I happen to be from Africa, so I guess for me, this is a home talk. The topic of my presentation is about charge. Charge very much as we use them in string compactification. And usually we compute them with different techniques. And so I'm going to introduce a method that generalizes what we usually do. So here I will be giving a whiteboard talk. So this is about, sorry, 1 second. Okay, there we go. So this is going to be about, 1 second, let me set it up. Okay.
Okay.
Okay, good. I had a problem setting up the pen, but it's working now. So this is going to be about matter representation and the GLSM technique. So the first question to ask is, why do we care about matter representation? And when you do a string compactification, typically you have a geometry, and out of the geometry, you try to derive the physics. And when you try to derive the physics, there are few elements that you care about. So the first one is to identify what is your gauge group. The second one is to know what are actually the matter that you see in your theory. And using different techniques, there are different approach to this. So historically, you had the heterotic string compactification. And in the heterotic string compactification, finding the group and the matter representation was relatively straightforward. Then you had compactification using F-theory that are very geometrical. In F-theory, you can determine the gauge group by looking at the type of fiber you get. So for example, if you have a fiber like this, that are singular fibers of an elliptic vibration, this is an affine Dynkin diagram of type A3. And so this would be related to an SU3 gauge theory. So as you consider more singular fibers in higher codimension, you can have some enhancement. So for example, this fiber, so this is an SU4, sorry, this fiber can enhance to a fiber of type A4. And this will correspond to a matter in the adjoint representation. So how do I know that? So the decomposition of the adjoint will give me matter in the fundamental representation. So how do I know that this is the case? That's when the Katz-Waffa techniques kick in. So Katz and Waffa were trying to find a method to detect matter without using duality to the heterotic string. So the way they deal with it, if you compare the picture I drew before, is to basically assume that when your fiber enhance, they correspond to different Lie algebra, and you try to understand the decomposition of the adjoint. So that means you have some Lie algebra G, that is a subalgebra of another Lie algebra H, and you try to see what happens when you decompose the adjoint of H. So typically, you will have the adjoint of H will give you the adjoint of G plus some representation that you call your matter representation. So in this decomposition, there are a few things you have to be careful about. So number one, the multiplicity that you see in the Katz-Waffa decomposition, they don't necessarily correspond to the physical multiplicity. So what it means is that the representation should really be think in terms of the reduced representation. So you basically see what are the reducible components, and then you will use other techniques to know their multiplicity. So for example, you can use, if you are in 6D, you can use the condition that you get from anomaly cancellation to find what the multiplicity are. And there are different counting techniques that works. So now in the original Katz-Waffa technique, G and H are very specific. So they typically look at ADE type of Dynkin diagram, and they also working with the condition that typically the rank of H is exactly the same as the rank of G plus 1. So you basically have rank 1 enhancement. So under this condition, they also observe the following thing. The representation R that you get will be a collection of irreducible representation. And these irreducible representation are typically they're typically representation that are called minuscule or quasi-minuscule representation. And so this type of representation are very rare, and they are very special in physics because they show up all over the place. But there is a little bit of a problem with this. A lot of interesting geometry that you would like to consider in physics are not of the type ADE. Clearly, you can have exceptional group like G2 and F4. And when that is the case, it's not so clear what you have to do. So there is an interesting work by Morrison, where, sorry, 1 second. So there is an interesting work by Dave Morrison and Antonio Grassi, in which they basically look at the geometry of F theory to try to understand what happens in all the other cases. And so what they had to do was to take into account the fact that in the geometry you have some fibers that are exchanged with each other, and they use it to try to determine the representation you have. But it's a little bit like you need to introduce a recipe for every new cases. So what I would like to propose today is a technique that is a direct generalization of a Katzbach. It's extremely natural and helps to actually understand matter representation in physics without necessarily attaching it to a theory or another theory. It's really something that has to do with the structure of Lie algebra themselves. So in order to explain this, I first need to review some property about representation of Lie algebra, and also subalgebra of simple Lie algebra. So the first notion is the notion of an embedding. Yeah, so I just dropped my tablet before this talk, and so as you can see, it does not write as good as it's supposed to do. So when you talk about two algebra G and H, the idea that G is a subalgebra of H is very ambiguous, because you can have multiple versions of G that are actually isomorphic to each other, but do not end up giving you the same representation when you decompose the adjoint. So this situation is visible even in very simple case. So let me take the case of A2. So in A2, the only Lie algebra you can put inside is A1. And already at this level, you can see that there are two possibilities. So if you think of the Lie algebra A2 as the parent Lie algebra, it has two possible subalgebra that are both of the type A1. However, if you do the decomposition of the adjoint of A2 along the first one, what you will get is the following decomposition. So you have the adjoint, which is the 8 of A2, will be written as a 3 plus the representation 5. And in the other one, you will have the adjoint would be written as the adjoint of A1 plus twice the fundamental representation plus 1. And so the one that people are familiar with in physics is this one. And the one that people will be very surprised to see anywhere is this one. So now clearly the one that is on the right is the one seen in the Katzbach technique. And so one should ask the question, what is the difference between these two embeddings? So when you talk about embeddings of Lie algebra, there is one number that characterize the embeddings in a way. It's called the Dinkin index of the embedding. So in this case, what we notice is the one that works has Dinkin index 1, and the one that does not work has Dinkin index 4. And so here you already see that the physics seems to make a choice, that when you have different options, it seems to select the one that has Dinkin index 1. And so one can then ask the following question. Is this an accident, or is this something that is true in a more general setting? So together with my collaborator, Monica Kang. So Monica Kang was a PhD student at Harvard Physics, and now she started this year as her first year of postdoc at Caltech. So we did a lot of study of enhancement of singular fibers in F-theory. Some of this research is also in collaboration with Xing Tong Yao, who is in the audience, Patrick Jefferson, and Shuheng Shao, who gave a talk on Monday. And so we have a lot of data to see what are the representations selected by the geometry. And out of this, we're making the following conjecture. The one that are selected by physics in the generic case will basically have Dinkin index one. And so this is the conjecture. And so the rest of the talk, I'm going to try to convince you that this is actually true. So the first case to consider is just the case of Katz-Vafa. So in the case of Katz-Vafa, what we have is we have 10 possible geometries that they consider, and they are basically all of the type ADE. So I'm going to review them very quickly. So in the Katz-Vafa technique, you have the enhancements of type AN-1 goes to AN that give you fundamental matter. You have the enhancement of type AN-1 goes to DN. You have A5 goes to E6. You have D5 goes to E6. E6 goes to E7. D6 goes to E7. A6 goes to A7, which I write here because it would be a 2E7. It will be a special case we will review, and E7 goes to E8. So all these are the representation that everybody is familiar with in string theory, and not a surprise, they all have Dinkin index 1 when you compute the matter representation that you get. However, you have to be careful of some boundary cases that are usually not considered carefully.
Hello, Isola?
Yes?
Okay, sorry, your voice disappeared for a while. Go ahead.
Okay, so the boundary cases are going to be the geometry that we studied just before. So when you have A1 goes to A2, you have a special case like this, but you also should be careful with A1 plus A1 goes to A3. And so you can think of it as a case where, for example, you have 2SU2 that enhance into an SU4. So in that case, you will also have a situation where there are multiple embeddings, and you have to be careful to select the one that is given by the physics. And so I'm going to give you a representation of A3, and it's all these subalgebra that will make the choice very clear. So if you consider the Lie algebra A3, it has three subalgebra of codimension 1, B2, A2, and A1 plus A1. So these are the maximal ones. So now let's be careful about the Dynkin index that they have. So I will put the Dynkin index as a power for the Lie algebra. So for example, here I will write B21, which means that B2 has Dynkin index 1, A2 has Dynkin index 1 as well, and the A1 plus A1 has actually Dynkin index 2 and 2. So basically, when you have a direct sum, you can give a Dynkin index for each component. So then you go one dimension lower, you get a A1 that has Dynkin index 10. Here you have another one of codimension 1 that is A1 plus A1, the same Lie algebra is here, but it has Dynkin index 1, and it's a subalgebra of B2. So this is a very special. Then you have another A1 of Dynkin index 1 that is a subalgebra of these two. And then finally, you have an A1 of Dynkin index 2 that is a subalgebra of these two. And the last one is a subalgebra of A1, 4. So as you can see, there are like all kinds of things here that are available, but those that have Dynkin index 1 are those that I'm going to circle in red. And there are only 4 of them. So it happens that if you look at the decomposition of the two A1 plus A1 that you see, the one of Dynkin index 1 is the one that gives you the matter representation that you expect to see in string theory, which is the bifundamental representation. The one that has Dynkin index 2 will actually give you a representation that will be of type 3 times 3. In the same way, if you look at the other one that I circled in red, the matter representation that they give you will basically correspond to what you would expect to see when, for example, you have a physical model that has a Lie algebra of type B2 that enhance into an A3 and so on. So basically, by just looking at this graph, you have the list of all the representation that you can get when a theory enhanced to A3, and there is nothing else. So the idea here is that this type of graph, we call them geography of Lie subalgebra. And so this is based on the work of Dynkin, who did it even before Yang-Mills theory were a thing. And interesting enough, if you look in the original paper of Dynkin, you actually see that even the very notion of decomposition in the adjoint is present. So he looked at cases where he has an enhancement, let's say of H from G. And there is a leftover representation here, and he called it the characteristic representation. And in his classification of what are the possible Lie algebra that you can get that are embedded in another Lie algebra, this notion plays an important role. In the physics community, R here will correspond to what we will call the matter representation, but once again, with that, all the precision on the multiplicity of the irreducible component. So what we did with Monica was basically to continue Dynkin's work by trying to not only compute R for all the possible cases, but also see how one case embed into another. So I'm going to give you another example that is very interesting in F theory. And after that, I will formalize some of the math that help to do the classification. So here, I will consider the case of the geometry of G2. So if you look at the G2 Lie algebra, it has the following graph associated to him in terms of embeddings. So first of all, you can have an A1 plus A1 that enhance into G2, but this one has linking index 3,1. So in other words, you won't see this enhancement in string theory. Then you have one that is a SU2, an SU3, sorry, that has index 1, and this one, the matter representation that you get is actually something that we see in F theory. Then you have 3 possible ways to get A1. So you have an A1 that has linking index 3, an A1 that has linking index 4, an A1 that has linking index 1, and one that has linking index 28. And the one that has linking index 28 is very special because it's actually a maximal embedding, meaning you cannot put a Lie algebra of dimension 2, of rank 2, in between G2 and this one. And the way they are embedded into each other is as follows. So here again, you can identify those that, according to our algorithm, will play a role in physics. So this is these 2 enhancements, and the matter representation that they produce can be explicitly obtained using F theory. And so basically, you can do this for all the Lie algebra. It becomes a little bit involved when the Lie algebra is big. However, it's doable. So for example, if you think of the Lie algebra E6, so E6 is a huge Lie algebra. It has 100 of sub-algebras that you can think of. However, those that have linking index 1 are only 30 of them. And they can be organized in a very beautiful graph. And understanding each one of them is basically interesting because the conjecture tells you that all the representation that you can get that gives you matter coming from enhancement of E6 would be one of these 30. So now I'm going to talk a little bit about the mathematics that is used to understand the structure of this graph. And the good news is that this is extremely simple representation theory. So the first notion is to not think of Lie algebra as a subset of each other, but really think about the map. And this is a notion that is very general in mathematics, in category theory, in algebraic geometry. We really like to think about math in terms of maps rather than just objects. So here, the most important notion is to have an embedding. And so what it means is that one Lie algebra can be mapped into the other in such a way that the map is injective. And the image of the Lie algebra G in the Lie algebra H will actually be isomorphic to each other. However, it's possible that the same abstract Lie algebra G can be embedded in many different ways in H. And the linking index is one way to keep track of it. So number 2, you need to have a notion of equivalence. And equivalence of Lie subalgebra is extremely tricky because depending on the definition that you choose, you can have very different results. So typically, there is a relation that is just called equivalence. And so what it means is that 2 sub-algebra are equivalent to each other if you can find an inner automorphism of the parent Lie algebra that map one into the other. So I would say this is the more refined notion of equivalence, but however, that's not the one that is relevant to understand matter representation. You have another notion of equivalence, which is called linear equivalence. And what it tells you is that if you have a representation of the parent Lie algebra, the 2 subalgebra that are linearly equivalent to each other should give you induced representation that are basically related by a linear inner automorphism. And so this notion here is the one that is relevant for matter representation, because it tells you, even if these two algebra are not the same, they give you the same representation. So now that you have these two notions, you can introduce different concepts that tells you how hard it is to identify the matter representation. So number one, the simplest situation is the following: a situation in which G is unique up to a linear equivalence. So in this case, it means that there is no ambiguity in saying what is the matter representation associated to G. And so when this is the case, we call this a singleton subalgebra. So singleton subalgebra are really the most friendly you can think of. So once you try to identify the geography of a given Lie algebra, the technique is really first to try to identify the singleton subalgebra, because they basically give you no room for mistake. There is no choice. You only have one possible matter representation. After the singleton subalgebra, you can have a situation where you have multiple G that are isomorphic to each other, but are not linearly equivalent to each other. However, by miracle, they can still give you the same representation. So when this is the case, we call it Katzwaffer singletons. Because for the purpose of matter representation, they are basically the same. And here it doesn't matter what the Dinkin index is, but in most cases that we know of, they will always have Dinkin index 1. It's very rare to find a singleton subalgebra or a Katzwaffer singleton subalgebra that does not have Dinkin index 1. There are a few cases in E8, and we have a classification of that. When you are outside of this case, that's when the conjecture start playing a role, because you basically, this is the jungle. You have a lot of different representation to choose from. And here the conjecture tells you that if you focus of the one of Dinkin index 1, you basically find those that give you the right representation. So I'm going to give you an example from F-theory, where this resolves like a situation that is very annoying for geometers. So you have the Lie algebra G2, F4 that are exceptional Lie algebra that are not simply laced. And it was always very annoying to try to understand the matter representation. So in the paper of Morrison and Antonella Grassi, so what they do is they try to identify one specific enhancement that gives you the matter that you would expect. But the matter that they get is the correct matter. However, the enhancement does not correspond to what you see geometrically. So what I mean by that is that you will, for example, think of enhancement where F4 goes to E6, and they actually get the matter representation from this. But if you look at the geometry of the F4 fiber, that basically is a symmetrization of the E6. So I'm going to draw a few diagrams. So this is G2 with the free node identified. And so if you look at G2 fiber, for example, the matter enhancement that you will get is of the following type, where these three nodes collide to form a fiber with multiplicity 3. So this, you can think of it as a fiber that is basically a reduction of an E6 fiber. And so for F4, you have a geometry that is a little bit more involved. So you have something that looks like a E6 with the nodes that are identified, and the multiplicity goes like 1, 2, 3, like this. And after you collide them at a singularity in higher codimension, what you get is a fiber like this. So according to the algorithm of Grassi-Morrison, you will get your representation from E6. But when you look at the fiber you get, this fiber is not a contracted E6. It's definitely a E7 or a E8. So it means that the proper way to find the matter representation of F4 would be to find it as coming from E7 and E8. And you can very carefully study the geometry, the geography of E6, E7, E8, see all the possibility of having F4 embedded in them. And you will see that those of Dinkin index 1 give you the correct geometry. So now there are some exceptional situations in which the conjecture does not work. And typically, these are not generic configuration. So there is a paper by Watty Taylor in which he finds representation that are exotic and that are coming from higher four-dimensional singularities over what is already singular subvarieties. And in this case, you end up having tensor product of the fundamental representation of SU2, and these do not have Dinkin index 1. So in other words, the conjecture will work only in the more generic configuration. When your configuration starts having, for example, brane that wraps singular divisors, you can actually have representation that will not satisfy the conjecture of having a Dinkin index 1. So since this is a string math in Africa, there is one particularity that is really funny that I'm just going to tell you before to close the case. So if you look at the geography of E6, and you only look at those that have index 1, the graph basically looks like the map of Africa, and the Lie algebra A1 would be in what is Cape Town, where our host actually live, and Durban would correspond to A1 cross A1. So we have a beautiful, the northwest point of the Africa map would be E6, and you will end up with all the different geometry in E6 that correspond to the key point of the map of Africa. So we have a map like this in our paper that will come out sometime next week. So I look forward for more discussion on this. So I would like also to say that when the index is 1, in every single case, we could actually map the representation obtained with a specific geometry of an elliptic vibration. And so that's pretty remarkable, because you have to think that the number of representation you get and the number of subalgebra you get are really huge. So for example, if you look at the case of E6 that I was talking about, you actually have 118 different semi-simple Lie algebra in E6. However, so you can think that each one of these 118 will give you a representation, and you might think maybe they are all physical. However, those that satisfy the condition of having Dinkin index 1 are only 30 out of the 118. So the conjecture is really helping you to fine-tune what is possible in terms of matter representation. And out of this 30, for every single case that corresponds to an enhancement that you can see in F-theory, you could actually see that the representation you get from those that have Dinkin index 1 are always the one expected in F-theory. And originally we thought that something that will actually play a big role are conditions like if your subalgebra is a S subalgebra or R subalgebra. So these are notions that I use in the King theory of the classification of subalgebra, but all these things didn't really play a role. You can have S subalgebra that gives you matter representation that you observe in F theory, and this was not something useful. You can also think that maybe the only one that will show up are those obtained by removing nodes from a given Dinkin diagram, and that was also not the case. So the fact that you have this conjecture is extremely powerful in reducing the type of model that you expect to see in the theory. So I'm going to stop here.
Okay, thank you, Jonathan. And let's applaud. So now I'll mute you. Ask Kumrun, who has raised the hand.
Very nice talk, Mboyo. I have a question. Do you have a deep insight about what is the physics of Dinkin index 1 being the condition to get matter representation?
Well, that's actually the key problem that we have, because we could see that this is definitely what helps you identify the correct physical representation. But when you try to find the reason why that is the case, you really don't see any given reason. So I'm thinking there must be something that geometrically is very, very deep to have this number to play such an important role, but physically we could not identify what it was. We tried to find if in other part of physics, such Lie algebra, the subalgebra of index 1 play a particular role, and we couldn't see a single example where they actually were even considered special.
Huh. Okay, thank you.
Any other questions? Well, maybe I should comment on that. You know, this program that also with Clavers and Taylor, we stumbled over, which is the studying about higher and higher charges of U1 gauge fields in F theory. Those are exactly this you would call that non-generic examples, but they are there because you're specially tuning singularities of the meta curves, and that, you know, can give you other representation that are outside this classification that you're dealing with. So anyway, just a comment.
So that's actually an important comment, because the idea is that if you start with one that is so special that it does not have a Dinkin index 1, the moment you perturb it a little bit, it becomes one of the generic case, you see. So the idea is that the conjecture is for the generic configuration. So it means if you define a model with a given set of parameters, your parameters are basically the generic parameters. And in algebraic geometry, generic is very specific. So it means you are not imposing additional constraints. But in the model that you mentioned, there are a lot of constraints that are required to have this exotic matter representation, which means they are non-generic. And so the Dinkin index could be anything.
However, you know, when one is asking a physics question, what can, for example, F theory produce for you by dealing with, you know, most general singular structure that is allowed, right? Those are not examples that are excluded. Yeah, they may be measure zero compared to so many others, but nevertheless, those are allowed consistent applications in F theory.
Yeah, they are allowed, but they don't represent even 1% of the possibility. So what I mean is that all the cases that are not of Dinkin index 1 were actually obtained very recently. All the historical models, the models that you see when you do superconformal theories, all these models, they have Dinkin index 1.
Right, but anyway, yeah, I think we can continue that later. Any other questions or comments at this point? No. So let's thank Jonathan and Boyo again for this nice talk. Let me unmute you all. Okay. So this concludes the first session on Wednesday. And so I will now give the mic back to Jeff if there are any further comments. Thank you.
Thank you, Miriam. And thank you, Jonathan, for a very nice talk. I very much appreciate the geography at the end. Okay, so our next session will be chaired by Sakura, who I will try and find. And it will start on the hour. So we have about 18 minutes until the next talk.
Thank you.
Hi, Jeff.
Hi, Sakura.
Hi.
How are you?
Thanks. So I can see, just to be sure, I mute everyone and I unmute everyone, and I can, if someone actually wants to unmute themselves, I do this manually, right?
So I've turned off. There was a little bit of lag between the chair muting and unmuting individual people. So I've turned off the
unmute.
I've turned on the ability for participants to unmute themselves.
Yeah.
Okay, so you don't have to do that manually. You can just mute and unmute, clap, mute, and then any questioners can unmute themselves.
Cool. Excellent.
A little bit of
and the first speaker,
yeah,
I'm not sure whether he's here. Let me check.
The first speaker.
I'm here. It's me.
Excellent.
Yeah. Hi.
Hi. So I think you need to be made co-host as well. And then you can at least check that you can share your screen and everything's working. We still have time.
Okay, very good. So.
Is my screen sharing?
Yep. Yes. It has this little sidebar as well, but you could try to remove that, but it's not bothering you.
Yeah, I can't. It's just a technical issue. Here we go. I'm having problems with the video for some reason. Not essential.
So it may be that you have to first go on full screen and then share. At the moment,
Unfortunately,
it's
if I go on full screen, part of the Zoom thing covers my screen, and I can't see what I'm talking about.
Oh, all right.
So how bad is the?
It's not. It's fine.
Yeah,
We can
I mean,
definitely
you
work
see
with that.
you see this thing on the side, but
Yeah, that's okay.
I can eliminate. Is this the issue where my mouse is?
Yeah, the side issue that the bar.
Yeah. Okay, I can
Oh,
kill that.
okay. Yeah, this is perfect.
Yeah. Okay.
Cool. So we have still like almost more than 10 minutes.
Okay. I'm just gonna mute for a bit. I'll be back in a minute or two. I'll be right here.
Okay, welcome back, everybody, to the last session of the day. The chair of the session is Sakura Serfanameki from Oxford, and I'll hand over to her now.
Well, thank you very much, Jeff. The first speaker of this afternoon session is Tom Maniero from Rutgers, and he'll tell us about the secret topological life of shared information. So please, Tom.
Thank you, and thanks to the organizers for putting this together. So I'm going to give a talk that's a little bit more quirky than the usual sort of talk that's given in string math, but hopefully it'll be sort of an interesting thing for everybody, and I hope it could be of use to you. So I'll be talking about a particular aspect of shared information, particular topological aspects that maybe you haven't heard of. And so we'll begin with the data of a multipartite state. And so this can be a state on the tensor product of some Hilbert spaces, or maybe a density state on a tensor product of Hilbert spaces. Or if you're not a hardcore quantum mechanic, you can consider something like a probability measure on a product of finite sets. So here, omega just denotes a finite set. And from this data, we can compute the mutual information, so the information shared among all the subsystems. So here, P indicates the sort of primitive tensor factors of the system, the primitive subsystems. And if P is equal to 2, and we're considering bipartite states, for instance, bipartite mutual information has become somewhat famous recently in the holographic literature. And you can actually generalize this to a multipartite version of shared information. And in general, it's a real valued quantity. And the claim of this talk is that this is actually categorified. So that means that there exists some graded vector space in this instance for which the Euler characteristic behaves like mutual information, or it actually is mutual information. And the cool thing about this is that while mutual information tells you about how much information is shared, this graded vector space tells you exactly what information is shared. And it might actually be non-trivial even when the mutual information vanishes. So bipartite mutual information usually doesn't vanish when there are non-trivial correlations, but the multipartite version can. And that's just like how the Euler characteristic of a topological space can vanish even when there's interesting gluing. It's a non-trivial topology. And in fact, there is sort of a non-trivial, non-commutative geometry or topology associated with this multipartite state for which cohomology captures this graded vector space. And the Euler characteristic of that non-commutative geometry is mutual information. Okay, and so for those of you who don't like or field theorists and or worry that this only applies to tensor product systems, it can also be applied to something in field theory, which is something like a local net, which is just an assignment of C-star algebras to causal diamonds or spatial slices of space-time. And this doesn't necessarily have a tensor product structure when you're considering multipartite objects. But all the technology here applies there. I'm just focusing on the tensor products version of the story, just for examples. Okay, so let's go back to our little diagram where we associate this graded vector space to an n-partite state. And I'll denote the graded vector space by hk of the n-partite state. So that's the kth graded component. And this is just knowing that it looks like cohomology. And this will capture tuples of k+1 body operators that exhibit some non-correlations, non-local correlations between subsystems. And so here k+1 body just means that the operators only act on k+1 tensor factors, non-trivial on k+1 tensor factors. And then we'll mod out by some sort of trivial correlations. So there's some operators that look like they exhibit correlations, but there's something like the identity operator or something silly. Okay, and this cohomology is great, or this graded vector space is great because it vanishes whenever we have, for instance, a pure factorizable state. And it also captures something like EPR pairs. So here I have the Bell state, a very simple entangled state on two subsystems. And this is a pair of operators which are sort of completely correlated. So these are two observables such that if you A measures this observable and B measures this observable, their answers are always completely correlated. And this cohomology captures all such observables. In fact, they might not be observables, they can be more general operators, but it also captures all of the observables as well. And more generally, if I have a bipartite density state, I'm going to, that cohomology is going to be generated by pairs of operators, RA and RB. So here I'll denote an operator by R just to indicate it's supposed to be interpreted as a random variable. And these two things are in the cohomology if and only if they obey this relation, which is saying that, well, if these two things were self-adjoint operators, it means that you can always replace RA with RB for all purposes of computing correlations, or even just, it's saying that RA and RB are maximally correlated in the sense that this EPR pair is correlated. Oh, sorry, this is, I have to resize my window here. Sorry for the technical issue. That wasn't apparent when I first began. Okay, I'll just do this for now. Okay, so what could this look like for higher cohomology? So let's consider a tripartite state. Well, the cohomology is going to capture triples of operators in this sense, where here RAC is just an element of the algebra associated to the subsystem AC. And these things will obey some linear relation like this. And the twiddles just mean that we have to lift these operators to the whole ABC system in order to make sense of this relation. And this twiddle, it also means that this twiddle, the other twiddle, means that they're maximally correlated in the sense that I described on the previous slide. Okay, so just to make this seem like it's a real thing, here's an actual example of a non-trivial cochain in the cohomology of the GHZ state. Okay, so why is this cool? Well, as I sort of mentioned at the beginning of the talk, I alluded to, cohomology has advantages over mutual information. So the bipartite mutual information, which is a alternating sum of entropies, measures some information shared by A and B. And it's a pretty good measure because it's non-vanishing whenever you have entangled states. And you can generalize this thing to the multipartite situation in a particular way. So what you do is you take this inclusion-exclusion sum pretty seriously, and you get an alternating inclusion-exclusion sum, just generalizing it. There's more than one way of generalizing bipartite information, but I'm going to be considering this version. And this in general is a real number. And it's supposed to measure the information shared by every subsystem, but unfortunately it's a little unreliable. So if I calculated this thing for these two entangled states on these tripartite entangled states, it vanishes, which sort of makes you think that, well, perhaps one system sort of splits off, it factorizes. But it doesn't. We know these things are entangled. On the other hand, the cohomology does capture something interesting here, and it'll tell you about the non-locally correlated operators. And so let's go back to this picture where we assign a geometry to the n-partite state, so one level higher. Directly from this geometry, we can calculate an Euler characteristic, and I'll just demonstrate how you can do this. And it turns out that the Euler characteristic is not just some integer. The right idea is that it turns out to be some holomorphic function. It's actually a holomorphic function in 3 parameters. So it has a lot of data in it. And this thing I'm just calling the state index. So it's just an Euler characteristic of some form. And from this holomorphic function, you can recover mutual information by taking some limits. But on the other hand, I can take some other limits and I get actual integers. And these should be the Euler characteristics of some complexes of vector spaces, which are the Euler characteristics of the cohomology I was talking about. So the state index encapsulates a lot of information. Okay, and so we should think of this vanishing of this multipartite information on these states, while the non-vanishing of cohomology is analogous to how when you take the Euler characteristic of a compact 3 manifold, you always get 0. So it doesn't tell you anything interesting. But the cohomology could be non-trivial because you have non-trivial compact 3 manifolds. So the idea is that cohomology only detects the number, Euler characteristic only detects the number of things that are glued together. And so for 3 manifolds, Poincare duality tells you, oh, you always have to get 0, but the cohomology can actually detect the gluing data. So just before we start defining things, I should mention that this is talk about basic quantum mechanics. Let's go back to our graduate school days and keep an open mind about things. There's very little input physics, which you might consider a bad thing, but it's a great thing because it's so general. And so there's no a priori geometry on any subsystems or tensor factors. I'm not talking about ADS-CFT or anything holographic. It's just everything sort of emerges out of just basic linear algebra. And I think this generality means there's something deep there. And one almost immediate application that I can think of is that you can actually generate link invariants in this way from this technology. So if you take a link inside of the 3-sphere, for instance, and I consider its complement, which requires a choice of framing or a tubular neighborhood, but let's just choose one. Well, if the link has n components, it lives in the tensor product space assigned to the torus, if I consider this on Chern-Simons theory. Okay, so I get a pure state on Chern-Simons with some gauge group given by this assignment here, and it lives in the tensor product of Hilbert spaces assigned to the torus. Okay, and now I can just use the technology I talked about, the cohomology, to generate Poincare polynomials, for instance, or just compute these state indices. And these quantities are invariant under the choice of a frame. And so they're link invariants. And I honestly don't know if they're related to anything known. So there's also some closely related work along the lines of the ideas in here. There's this cute little paper of entropy as a functor, which has some sort of ideas that I also bring up. There's the most closely related work is by these fellows, Pierre Bourdeau and Daniel Bennekin, which talk about how mutual information in the classical world of probability theory actually arises as sort of a characteristic class. So they don't say it that way, but this is what they're saying. It's some obstruction theory thing. And their student, J.P. Vigneault, actually provides a nice exposition of this work. And this should actually tie into my work if you, it needs to be rephrased in a more modern language of obstruction theory to see the connection. I'm hoping to do that in the future. Okay, and then some folks also talk about applications of homotopy techniques to probability theory, and that has the same sort of flavor of what I'm talking about. Okay, so I should describe what a state is in my talk. It's something very general. So I'm just going to think about positive linear functionals on algebras, which are the expectation values of some measure or some density state, for instance. And if you want to get technical, I'm really generalizing everything to infinite dimensions. And I'll be focusing on finite dimensions, but you can generalize most things to infinite dimensional situation with von Neumann algebras. And technically, I'm using the abstraction of a W-star algebra. So you can use these two interchangeably. So for instance, if you're a pure quantum mechanic person, I can just consider this algebra, which is the algebra of random variables, to be bounded operators on a Hilbert space, and you get density states. On the purely classical side, I can consider functions on a finite set. And there, the state is just a measure on that finite set. I can consider the infinite dimensional version of this. Or I can consider sort of a quantum classical mixture, which is just a product of matrix algebras. So all finite dimensional W star or C star algebras look like this. And a state on this thing is just effectively the same as a tuple of density states. So one density state per factor of the matrix algebra. And this example, even if you don't care about quantum classical mixtures, sort of, if you look deeply at what some of the things I'm going to say, emerges naturally, even when you consider just the purely quantum mechanical situation. So keep it in the back of your mind, maybe. And it actually specializes to this case of the purely classical situation when you consider only Hilbert spaces that are one-dimensional. So you just end up with a measure on a finite set. Okay, so what's a bipartite state? Well, it's just the data of a pair of algebras and a state on the tensor product of those algebras. And when I want to be lazy, I'm just going to denote this with this whole set of data by an underline, and then maybe the subsystems that it lives on. Or I'll just say that rho is a bipartite state on this tensor product. And well, I can pull this state back on this tensor product using these to the individual algebras associated with the subsystems by using the tensor bi-identity maps. And this gives us reduced states or partial traces, or if you're talking about measure theory, the reduced measures, it should be, say, reduced on all the subfactors. Okay. So this is the real structure of what I mean by bipartite state, is these pullbacks. It's not necessarily just the tensor structure. And we say this thing is factorizable. Well, if it factorizes as a tensor product of its linear functionals, And there's some normalization factor if we consider unnormalized things. And well, a pure state is factorizable if and only if it's functional is factorizable. And in the classical world, the question of factorizability is about the question about independence of random variables. So similarly, you could talk about multipartite states. It's just the data on a tuple of algebras, data of a tuple of algebras plus a state on that tensor product. And similarly, I'll denote that by an underline. And again, for any subset, now I can pull back that state to the algebra associated with that subset. So you just take the tensor product over the subset. And I'll denote that by rho sub t for the subset t. And I should also mention, because everything in this talk is sort of functorial, everything is invariant or equivariant under local automorphisms. So these are just transformations of the state by a tensor product of an automorphism on each of the primitive subalgebras. So in particular, this is like changing a state under local unitary transformations. I'm actually considering things that are more general than unitaries. They can be invertible instead, but you can actually change the story up and just talk about unitary transformations as well. Okay, so let's see why geometry should be associated to a bipartite state. And this diagram is sort of helpful for seeing that. Well, the idea is that if our state is factorizable, if I want to compute the expectation value of any operator, if I decompose that operator in the tensor product basis, I can basically just glue together expectation values on the local of local data, of local expectation values. So if I just know all the expectation values on the reduced states, I automatically know how the full state acts. So an obstruction to this descent of expectation values is basically encapsulated by pairs of operators that don't factorize in this way. And so that should set off your homological alarm bells. I use this this language obstruction I used it intently. And so you should expect that the cohomology captures these obstructing operators. So, and more precisely, it turns out that it actually captures those operators that are maximally correlated. So just not vague statistical correlations, but maximal correlations. And then I mod out by, for instance, the trivial correlation, which is just the two pairs of identity operators. Okay, so let's go back to mutual information and get another inspiration for why there should be some geometry behind this. So here is our bipartite mutual information. It's a positive real value quantity. And if you want to know the details, I can define entropy for a state on this product thing like this. And this is the same thing as the Iraqi entropy for finite dimensional algebras, for instance. And it generalizes the notion of a Shannon entropy and von Neumann entropy. So I just take the sum of all the von Neumann entropies on each individual density state. Okay, and so I'm only going to be talking about normalized things here when I talk about entropies. You can generalize entropy to non-normalized things, but it's getting a little funky in terms of physics. And I can take this, as I mentioned before, I can take this inclusion-exclusion sum and generalize it to define multipartite mutual information. And it's not going to be a positive value quantity anymore. But the nice thing about it is that it can detect whenever the state factorizes. So if I have a tensor product of multipartite states, for instance, an n-partite state and an f-partite state here, this tensor product is n times f-partite state, it will vanish if it's a tensor product. So this thing will vanish if any system decouples. And so it's a good detector of decoupling. And so the converse of that is that you have to have something non-vanishing that it means nothing could decouple. And well, we know for the bipartite mutual information, the converse holds true. But for more than 3 subsystems, as I mentioned before, you have tripartite informations that vanish for n greater than 3 more generally. And you could just actually advantages on a whole family of states. And well, that's not a great thing. So let's try to understand what's going on there. Well, the idea was that it comes as an Euler characteristic, and maybe I can generalize that Euler characteristic as coming from some cohomology. So in fact, it looks like an Euler characteristic. And this might be a superficial observation, but it turns out to have a very deep meaning. And you just sort of reorganize the sum in a particular way. And it looks like, well, if there is some geometry associated to the state, perhaps this quantity here is the dimension of some kth component of the geometry. So I'm thinking of the geometry of the state as built up something like a CW complex or a simplicial complex, or maybe even a chain complex. So here, this can be just the kth component. And this fellow is the dimension. And so it encodes all the data about the partial traces here. So this I just want you to keep in mind. But this is just some vague observation. So let's try to make this more precise. Let's assume that there is some geometry, and we have to figure out what's the Euler characteristic associated to that thing. Well, first I have to tell you what I mean by Euler characteristic. And by that, I'm just going to be very general. So I'll just consider a category of some geometric objects. And all I really need here is a tensor category and some ability to glue those objects together. So if you know what this means, a push out, you have all push outs. And then an Euler characteristic valued in some ring, this should be a D, sorry, this is a ring D. An Euler characteristic valued in some ring is just an assignment that takes in isomorphism classes of those objects and outputs elements of the ring. And it should play nicely with tensor products. And it should obey this inclusion-exclusion relation whenever you have gluing. So here X and Y are objects, and I'm gluing along Z in some sense. And it's just this inclusion-exclusion sum. But notice that it doesn't care about the details about the gluing along Z. So that's both a good thing and a bad thing, because we're losing information, but also it makes it easier to compute. So I can probably glue X and Y many ways along Z, but it doesn't care about those. And you can phrase this in a different way. You can just say an Euler characteristic valued in the ring D is just a homomorphism out of the Grundy group of the category. So that's the same sort of concept of these relations. Okay, so some quick examples. You take this idea on finite sets. This is just the Euler characteristics of the cardinality. Finite vector space's dimension. If you take graded objects, you get these alternating sums. And those are valid Euler characteristics. But I can also get things that look like Lefschetz indices. So if I consider, for instance, some category generated by pairs of vector spaces and endomorphisms, and I'm not describing the morphisms, but you can write down some pretty natural things, and you always get the same sort of Euler characteristics. Here, a good family of dimensions is just given by the traces of powers of the endomorphism. Or you can just think of this, actually, the whole dimension is collecting into a function on the positive integers. And then I can also get Lefschetz looking things if I take graded versions of this. So let's go back to our category of, well, we're going to suppose there's some category of multipartite states. And perhaps this geometry that we're assigning to the multipartite state is just some tautological functor. And so really, what I'm saying is that the category of multipartite states is perhaps the geometric category we want to consider. And that just means that we can compute this Euler characteristic directly in terms of the multipartite state, without first having to understand the geometry associated to it. And now, to sort of understand how this Euler characteristic might look, we use a little bit of intuition here, and we can think of the bipartite state as being glued together by unipartite states, the reduced states, along the system AB, using the data of rho AB. And so this little identity, you could just write down with this sort of diagram. And here, these are Euler characteristics of unipartite things. And we can just repeat this recursively for n-partite states to express everything in terms of unipartite states. So just Euler characteristics of states on a single system. And well, okay, it's already starting to look like mutual information, but that's just because it's an inclusion-exclusion sum, nothing fancy there. And it's actually convenient to think of the dimension of a state as sort of the Euler characteristic on the unipartite thing. There's no alternating sums, it turns out, for these things. So it's just a change in notation. And if I want the Euler characteristic of multipartite things to factorize, the dimension has to factorize in a nice way. So let's take a guess at what this dimension is. Well, you want this to look like mutual information, but unfortunately, entropy doesn't obey this relation. It obeys this with a sum. So you say, oh, well, okay, I'll just take the exponential of the entropy. But that actually also has its own set of issues with playing nicely with the inclusion-exclusion sum. So more generally, you can look at this for a while, and you can write down something very general that does work. And it's this fancy looking quantity. And it depends upon three parameters, alpha, q, and r. And it's just given, so there's a lot of data going on here. The thing to sort of note is that it looks like one of these Lefschetz indices where I can take arbitrary powers of this state. And so here, since everything is positive, semi-definite, or positive, this makes sense on all complex numbers, and it becomes an everywhere holomorphic function. And I can extend this to states on a finite dimensional algebra by just taking the sums of the individual dimensions of the density states. Okay, and so with this in mind, I haven't gotten to multipartite information yet, but I'll show you where it comes from. We can define, it's actually somewhat convenient to introduce the density state on the empty system, which is just the identity operator, maybe with some rescaling if we're talking about non-normalized things. And then there's some silly sign. And it's basically the same thing as the Euler characteristic. It obeys this nice relation. It obeys some nice gluing relations. But the cool thing is that if you rescale it and take some limits, it captures mutual information. So in general, this rescaling gives you this alternating sum where the entropies are replaced by deformed versions of those entropies. And here I'm calling this the Salas-Rényi deformed version, depends upon two parameters, because certain limits recover the Rényi entropy, which is pretty famous, and they also recover this Salas entropy, which has been a little neglected in the literature. And if I just take the limit q that goes to 1 of this thing, no limits on r are required, I recover the standard classical mutual information. So here's a diagram showing that. There's a lot of things going on here, but the thing just to note is I can start from the state index, which looks like an Euler characteristic of something through our vague discussion, and I could take a limit and get mutual information. But if I take another limit of these parameters, I start getting integers. And so we might think that there's some vector space associated to the state where this dimension quantity captures the literal dimension of that vector space. So in fact, there's a certain thing that assigns a vector space to a state, and that's the GNS construction. So let's talk about that. So recall that the GNS construction is just a way of assigning a module for a particular algebra given a state. And the way you do that is you just take your state, you look at this ideal of vanishing vectors with respect to that state, and you quotient out by it, and you get a left module. And just as examples, this will look something like functions. This should be a mu here. If I have a measure on a finite set omega, this is canonically isomorphic to functions that are on the non-vanishing points of the measure. And in finite dimensions, this is just some easy-looking vector space in terms of the density state. And the dimension actually turns out to be given via specialization of this dimension function. Okay, so we're on the right track here in terms of figuring out whether or not these Euler characteristics come from complex of vector spaces. So how do I get this complex of vector spaces? Well, you can actually, here's the fancy stuff. You can actually get this by looking at the GNS construction as a functor. It elevates to the level of a functor. And so you can define a category of states, and you can think of these as the unipartite states. And it just takes you into some category of representations. So here the objects are just some states. And on the other side, I get algebras and left modules. So the algebra can vary in both of these things. And the morphisms you should just think of as partial traces on the state side. Really, they're duals of algebra maps in some sense. And on this side, I get algebra maps and intertwiners. And both of these categories have nice notions of products and coproducts. So here it's just the product of both the algebras and the modules. And on this side, you get some sort of classical sum. And you can think of this as sort of like these sort of quantities will arise even if you're a pure quantum mechanic, if you're considering, for instance, super selection sectors or measurements of a subsystem. These classical sums can be somewhat convenient. Okay, and well, how this thing acts on morphisms, if you know these terms, it's actually related to relative modular flow. But the thing I want you to focus on is that it actually takes these coproducts to products. And if you look at what a multipartite state is deeply, you can also think of it as a functor into the category of states. So it's sort of like a pre-sheaf. And it takes a subsystem into the reduced state. And then for an inclusion, so this is the category where the objects are subsets and the morphisms are inclusions. It's just a poset. And it reverses the inclusions by considering the partial traces over the complement. And then, so from this construction, you can just use check theory to construct something that looks like this. So this is called a simplicial object. So basically, if I start from a multipartite state on all subsystems here, I just take the traces over all one element systems to get a bunch of partial traces. And so this is, this is all fancy. I don't expect you to understand exactly what it is. But the point is that this is our geometric object associated to our state, our multipartite state. And the kth component is given by this classical sum of the reduced states. And if I take the Euler characteristic of this thing, well, this is how we recover our state index up to some sum. And so, yeah, I'm also including this extra augmented piece of the empty state on the empty system. Now, how do I get a chain complex from this thing? Well, this is where the GNS construction comes in. I take this, and it just reverses all the arrows. But now each of these things is just a module. So something more realistic. And then I just forget about the underlying algebra, the module stuff, and I just think of them as vector spaces. And I take an alternating sum of these arrows. And it turns out I get a chain complex out of that. And so you should think of GNS of rho t as a subset of the random variables on the system T. So there are particular types of random variables. You're quotienting out by trivial things that you can't detect through the state. So what does this look like for the bipartite system? Well, it looks something like this. The point to focus on is that this differential just looks like this sort of this tensor product with the identity, and then I take a minus sign between the two. And so if this vanishes, it just means that one tensor B and a tensor 1 are sort of like the same thing. The state cannot detect the difference between the two. So they're maximally correlated in that sense. So that's what the zeroth cohomology captures. And for a pure bipartite state, you can actually compute this thing explicitly, the cohomology, in terms of the Schmidt decomposition. And if you're wondering what the first cohomology encapsulates, well, the dimension is a measure of how far the thing is from being maximally entangled. So there's a whole commutative version of the story on measures. And it turns out that the GNS construction actually gives you a commutative algebra when you're considering just commutative objects. And then I can use a version of spec to recover a set from each of those algebras. And the result is that you get something called a simplicial set. You can just imagine as a simplicial complex. And the state index of this actual topological thing, just its standard commutative geometry, is just a deformation of the Euler characteristic of this that takes into account the sizes on each of these simplices. So the weights, the actual values of the measure, you can think of as sort of lengths of certain edges on the simplicial complex. So here's just a picture I'm going to flash at you for how that might work, is that I consider a measure on two finite sets, and here's some weights so everything else, the measure is vanishing. So here y1, y2, and y3 are elements of some finite set, and the measure only vanishes along this, is non-vanishing along this diagonal. And to this picture, I associate a very simple looking picture where the lengths of these edges are given in terms of the logarithms of the weights of the measure. And then I can compute the generalized Euler characteristic, and at certain limits, it encapsulates the actual Euler characteristic of this space, which is 3. So just to summarize, mutual information it emerges naturally as the Euler characteristic of some canonically associated non-commutative space. And in the world of probability measures, this is not non-commutative, it's commutative, and it's just a simplicial complex. And you can actually figure out what the non-local correlations are in the state by just computing cohomology. The point to make is that cohomology is a finer invariant than mutual information because it can detect how things are glued together from this perspective versus how many things there are. So just a finer invariant. Okay. Some other comments is that there's a G equivariant version of this whole story. So maybe there's some G equivariant mutual information. And this is actually a smaller part of a much bigger story about the Kasparov construction. So you can replace the GNS construction with this more general Kasparov construction. And this is all related to this correspondence of two categories between some category of C-star algebras and completely positive maps and a category of C-star algebras and pointed Hilbert bimodules. And as a sub-story of this, in a separate work with Greg Moore and his student Roman Gayko, we're exploring the equivalence of categories between matrix product states and completely positive maps. And the hope is that this has shed some more insight on how low energy effective field theories of lattice systems are topological field theories. So it turns out that a natural notion of an RG invariant matrix product state is a Frobenius algebra object in some category, which you should think of as assigning a topological field theory. So there's some future directions we can think about what happens when we compute these cohomology of some states that arise from holography. Hopefully you get the geometries you get or something nice. Would this be useful for quantum information theory? It would be cool if we can actually generalize the proof of strong subadditivity, which is a relation between entropies that's somewhat difficult to derive for general infinite dimensional von Neumann algebras. And this was geometrically interpreted. There was a geometric proof of this strong subadditivity condition using the Ryotake-Yanagi formula, but it only works for holographic states. So hopefully this construction can actually give a generalization of that proof to just for general states. As I mentioned, it can produce link invariants. There's some generalizations perhaps of the Poincaré polynomials. So these are just vectors that encode the dimensions of the Hilbert spaces, which right now are just integers, but we should be able to generalize this to holomorphic functions. And there's a whole sort of correspondence of this stuff to non-commutative LP spaces and relative modular flows. And I understand part of this story, but not everything. And it'd be great to understand how that works. And I'm looking for future applications of this. Right now, it's just some very general technology, but I'd actually like to do some very interesting physics with it. And if you're interested and you want to get a handle on this thing, I have some software on my GitHub webpage you can check out. Okay, that's it. Thank you.
Okay, thanks very much, Tom, for this nice talk. I'll unmute everyone so we can clap. And let me mute all again. And other questions? I can see that Hank Chen has a question. I will unmute you and let's see whether you can.
Hello?
Yeah, Hank, you should be able to ask your question.
Hello, can you hear me?
Yep.
Okay, thank you, Tom, for the very interesting talk. So I'm just coming in from a more condensed matter sort of perspective where you were talking about Kapustin's work, right? Where you relate the matrix product states to the invertible 2D TQFT. So just from this understanding where you have these sort of interacting classification of topological orders on the right-hand side in your diagram over there, there's this associated map into free fermions, right? Where we can actually detect what happens to topological order as we take away interactions. Maybe there's, from your perspective, maybe there's also something analogous on the state side.
So you're saying I'm not sure, you're saying the free fermions are somehow associated to this side?
Yeah, on the right-hand side, there is a map. Yeah, so it's in a free Hopkins classification where they actually study these kind of maps for free fermions. Yeah.
Okay. Yeah. this is all relatively new. So yeah, there should be something corresponding there. This is a functorial equivalence. There's a translation of anything on this side to something on this side. So indeed, there should be something on this side.
Maybe I thought that it might be interesting to study that on the left-hand side as well.
Absolutely. That's the whole point of it. Yeah.
Okay, good. Thank you.
Just don't know what it is.
Okay, I don't see any other questions. Perhaps while everyone is trying to get the raise hand function to work, can I ask how far away are you from actually applying this to holographic systems? You had on your slide, the next slide, I think.
No. Right, yeah. So this is all relatively new. I've been just working on the technology itself, and recently my focus is actually on this correspondence, which is somewhat related to the entanglement homology. But indeed, that something that we'd like to apply this is just some very simple holographic system to see if you actually this geometry is related to the sort of emergent geometries you get out of holography.
Okay, thanks. I don't see any other questions. Let's thank Tom again. I will unmute you all. We will continue at 5 o'clock British summer time, whatever that is, where you are, which means in 20 minutes with Nathalie Paquette. So thanks very much, Tom. Nathalie, are you there already, by any chance? Nope. Okay. We'll take a break.
Okay.
Jeff, are you there? Hi, Natalie.
Yeah, yeah.
Hi, great. Could you make Natalie a co-host, please? I don't
Yes.
think I can do that. And then we can check out whether the slides work.
Okay, done.
Great, thanks.
Okay. Everything look all right on your end?
That seems to work. Very good. Great. And we still have 15 minutes, so
okay.
Just wanted to make sure we can take a break. And yeah, I'll be chairing you again, like 2 weeks after you spoke at the other.
Good. We have a system. It's going to run smoothly.
Yeah. Now we've practiced this already. Yeah.
Oh, great.
Okay, Natalie, are you ready? I think you need to unmute.
Yes.
Yeah. Okay, very good.
Yeah, ready when you are.
Yes. Okay. Just give me 1 minute. Okay. Jeff, do you want to make an announcement beforehand, or shall we just go?
I think you can just go.
All right.
I'll announce it in the chat.
Okay, fantastic. So our second speaker in the second Wednesday session is Natalie Paquette, who's in some state between Caltech IS and University of Washington. And she'll talk about twisted holography and causal duality. So thanks, Natalie. Please go ahead.
Thanks very much. And I want to thank the organizers for inviting me to this conference and for putting it together during this difficult time. I wish I could, of course, see all of you in person, but hopefully we'll be able to do that soon. So today I'll be connecting some toy models of the ADS-CFT correspondence with a mathematical notion called causal duality. And this work is in collaboration with Kevin Costello. So I hardly need to tell the attendees of this conference that string dualities are a rich source of novel mathematics or novel connections between different areas of mathematics. And there are, of course, too many wonderful examples to list, many of which have been discussed already at this conference, with, for example, mirror symmetry and its homological enrichment giving one precise instantiation of this idea. But we have an extremely rich physical duality in the ADS-CFT correspondence, from which we're learning a lot about quantum gravity, that I think it's fair to say hasn't yet permeated back to the mathematical community. And I think it's also fair to say that a better mathematical understanding, at least of some special examples of the duality, could be useful for us physically with respect to perhaps gaining some conceptual insights or learning new ways to think about or organize observables. So today, when I think about the ADS-CFT correspondence, I'll have in mind particular top-down models coming from string theory constructions starting in 10 dimensions in the presence of D-branes. And I think the audience is largely comprised of physicists, so all of this is very familiar stuff. But of course, roughly speaking, the ADS-CFT correspondence from this top-down perspective is two complementary ways that turn out to be equivalent of thinking about the same D-brane physics, again, being very cartoonish. So on the one hand, we'll have some stack of branes whose excitations are given by open strings, and in a suitable low energy limit, we have some supersymmetric world volume theory that's a quantum field theory that in our examples will be, in fact, a conformal field theory. And on the other hand, we can look at the geometric background of string or M theory in the presence of these branes. And again, in a suitable limit, we find a closed string geometry, a closed string background or a gravitational theory whose geometry includes an anti-de Sitter factor. So today we'll be trying to really describe some of the mathematical underpinnings of a toy model coming from one of these top-down constructions. So let me introduce now the hero of my talk. There we go. So the dual pair that we're interested in today is familiar, I think, again, to many people in the audience. On the gravitational side, we have type 2b supergravity or string theory in the background ADS3 cross S3 cross T4. And for much of the talk, I will be focusing on the strict supergravity limit where I'll be taking the string coupling to 0. And this is well known to be dual to a 2D conformal field theory, actually a superconformal field theory on the moduli space of the sigma model whose target is the Hilbert scheme of endpoints on T4, with the corresponding dual limit here being the limit that n goes to infinity. And well, closely related to the fact that this target space geometry is hyperkähler, the 2D conformal field theory enjoys two copies of the n=4 superconformal algebra, one holomorphic and one anti-holomorphic. So of course, there's a lot of supersymmetry in the game. And what we'd like to do is to exploit that and do what we often do when we try to make some precise connections to mathematics and study this duality in the presence of a certain supersymmetric twist. So the name of the game will be to start with this very rich physical duality and restrict to some protected cohomological subset of observables that correspond with some BPS observables in the full physical theory. And I'll say more about that on the next slide. And then ultimately, as we study this twisted toy model, we'd like to make some connections to generalizations of a mathematical subject called causal duality. So for us, this was a nice example to study for a few reasons. Firstly, it's a fairly technically simple example of ADS-CFT as these things go, in part due to the relatively low dimensionality of the theories involved, a 2D conformal field theory, 3-dimensional ADS space. And it's also been extremely well studied from a variety of perspectives. So as we try to probe this twisted version or this toy model, we were able to benchmark it against a lot of results that have been produced by studying the full physical or untwisted duality. So in spite of its technical simplicity, it's still quite physically rich, but nonetheless, in the twisted version, we have some hope of making some mathematical statements and hopefully gaining some new insights. So what's the twist that I'll be talking about today? Well, the kind of twist that I'll be discussing is a slight generalization of the more familiar topological twists that I think are, again, quite familiar to most people in the audience. So in addition to our usual BRST differential, which we use, of course, to restrict cohomologically to gauge invariant observables, to that we'll add an additional nilpotent supercharge in the theory Q and take the cohomology with respect to this total supercharge Q tilde. And if we imagine, for example, that we're studying a theory, say in flat space, where we view the space as complexified, for example, in 10 dimensions, 5 copies of the complex plane, and we endow that with holomorphic and anti-holomorphic coordinates, then we'll choose a supercharge that has precisely the property the translations in the anti-holomorphic directions are Q exact. And there are natural choices of Q also for the slight generalizations that we'll need. So this twist is often called the holomorphic twist, and it has also appeared in the literature in a few contexts. So we'd like to apply this twist to both sides of the dual theory and study, to both sides of our duality and study the results. Okay, well, on the 2D conformal field theory side, what sort of mathematical structure might we expect if we perform a holomorphic twist of this type? Well, if we're rendering anti-holomorphic translations exact with respect to our supercharge, or exact with respect to the cohomology that we're interested in, then the algebras of operators will have a position dependence that only depends on the holomorphic coordinates, possibly with some poles as the operators become coincident. And that's exactly the right kind of structure to have a vertex algebra or a chiral algebra on the CFT side, or perhaps something related to the chiral de Rham complex if there's a geometric interpretation in the case of a sigma model. Correspondingly, there should be a dual notion of twist on the supergravity side that we're able to make use of. And for the purposes of today's talk, we'll be assuming a conjecture of Costello and Lee, a conjecture for which I think there's a good deal of evidence, that describes what the appropriate dual notion of a twist is for the supergravity side, which of course has been a bit trickier historically due to the fact that supersymmetry is gauged in the supergravity theory. But Costello and Lee propose that we should think of the twist in the following way. They tell us that a twist of type 2b supergravity on, for example, a Calabi-Yau fivefold can be defined. There is a suitable choice of Q which has the properties that I'll need for this talk. And the resulting theory is the Kodaira-Spencer theory on that Calabi-Yau manifold, which might be already familiar to many of you as the closed string field theory or the target space supergravity theory for the B model topological string. And of course, this was studied by Bershadsky, Ciccati, Oguri, and Vafa. So already we see this idea that of the simplifying power of performing these twists. On the supergravity side, our degrees of freedom included all components of the metric as fluctuating fields in the theory. Here, we're restricting to some simpler and more tractable set of degrees of freedom. And the Kodaira-Spencer theory in particular is a theory that governs deformations of the complex structure. So we retain some of the dependence of the metric fluctuations, but only precisely those that modify the complex structure. So we're working in a fairly, in a simpler and more tractable physical setup than the original theory. Okay, so we've assumed this conjecture, but in particular, everything I've said required that the background that we started with was Calabi-Yau. And so it seems like applying this directly to ADS3 cross S3 cross T4 would be a little bit cumbersome. Or indeed, I haven't told you how one should do it. So to get around this complication, I propose that we do the following thing. Let's start life in 10 dimensions in our twisted theory and try to run in parallel the derivation of the ADS-CFT correspondence exactly as we would do in the physical theory. And I'll sketch how that goes. And then the hope is that doing this twist and then following through the ADS-CFT prescription are commuting processes. And hopefully this twisted model then will still capture salient features of the physical duality. So we'll run through this procedure, and then I'll explain some of the results or computations that one can do in Kodaira-Spencer theory in the aftermath, and we'll indeed see that the results we get from following this procedure seem to encapsulate some of the BPS physics of the full untwisted duality, which gives us confidence that this is a sensible procedure, and at bare minimum, it's giving us a nice toy model that we can approach mathematically. So let me remind you how this derivation goes, and we'll work in parallel between the physical and twisted duality, and I'll tell you what the result is. So as usual in the physical string theory, we start in 10 dimensions, and we'll consider type 2B string theory on R6 cross T4. I'll be in Euclidean signature throughout this entire talk. Correspondingly, we can start in Kodaira-Spencer theory on now C3 cross T4 equally well. So here, the twist that we're using is well defined. And to this system, we of course add our D-branes. In this particular example, one adds N1 D1 branes, wrapping a choice of 2-plane in R6, cross some points in T4, and N5 D5 branes, wrapping the same 2-plane in R6, and also wrapping all of the 4 torus. And similarly, one can add the same number of branes in the B model, now wrapping a complex plane, a choice of complex plane in C3. The next step is to perform the dimensional reduction on the 4 torus, so we can study the effective 6-dimensional gravitational theory that's coupled to an effective 2-dimensional theory coming from the non-compact directions of the brane world volume. We can do the dimensional reduction equally well in the physical and twisted theory, and on the next slide, I'll say a bit more about how that procedure works in this Kodaira-Spencer theory. But at the end of the day, one obtains, as I said, a 6-dimensional theory that's coupled to a theory of some effective strings given by these branes, and we'll define n as usual to be n1 times n5. So there's n effective strings in our theory. Now, crucially, the D-branes, of course, are massive charged objects. They couple to the closed string sector of the theory, and they will deform the geometry, as you all know. And in particular, the D1, D5 brane systems will source some Ramond flux that will deform the metric in the transverse space to the branes, and one can compute this back reaction and obtain in a suitable limit the ADS3 cross S3 geometry that we're interested in. So we need to do a similar computation on the B model side. Indeed, the B branes will source a field that descends from this Ramond flux, and it turns out that, as you might expect from the Kodaira-Spencer theory, it deforms not the full metric, of course, but the complex structure of the transverse flat space. It will do so in a way that's integrable away from the support of the branes, and will obtain a manifold that we call the superconifold, which I'll describe in more detail on the next slide. And of course, to complete the derivation of this duality, there are various judicious limits that one has to take, which are expected to be trivial from the point of view of this cohomology. So for our point of view, and through much of the talk, I will keep in my mind the origin of this dual pair is really arising from a coupled open closed string system, since these decoupling limits, the cohomology is not so sensitive to these decoupling limits. And this will be a useful perspective later, as I'll stress. Okay, so let me tell you a little bit more detail about what one obtains in the twisted theory, and in particular tell you how should you think of twisted to be supergravity on ADS3 cross S3 from this point of view? What's the resulting theory? Okay, so I claimed that the ultimate answer was Kodaira-Spencer theory on this manifold that I called the superconifold, so let me tell you what that is and how we got there. So here we are starting life in our 10-dimensional flat space. The branes are wrapping some plane that I'm endowing with a coordinate, holomorphic coordinate z, and let's give the transverse coordinates, transverse planes the coordinates w1 and w2. And I also have my 4-dimensional torus. So first, what's the result of the dimensional reduction on the 4 torus? Well, to tell you that, let me remind you about some of the basic properties of Kadeira-Spencer theory. Kadeira-Spencer theory is a theory whose basic degrees of freedom are polyvector fields that satisfy an equation of motion and a constraint equation, and also potentially a gauge fixing condition. I'm suppressing the various equations, and I haven't written down the Lagrangian, but these are well known in the literature. And in particular, polyvector fields on some manifold are nothing but 0J forms valued in antisymmetric powers of a holomorphic tangent bundle. So these are some basic geometric objects, and we're incorporating fields at all values of I and J, which for me is equivalent to keeping the full BV-BRST complex of Kadeira-Spencer theory. So implicitly, although I'm not being very explicit about the ghost number and details in this talk, I'm including ghosts, antifields, and the like, and really keeping this full complex. And again, that will be a point that will be a little bit more important later in the talk. Okay, but nonetheless, I have this theory whose basic degrees of freedom are these polyvector fields. And since I'm on a Calabi-Yau manifold, well, any Calabi-Yau manifold has a non-vanishing holomorphic volume form. So if you don't like polyvector fields, or for technical convenience, you can always contract these polyvector fields with my holomorphic volume form on the Calabi-Yau, and equally well think of them as ordinary differential forms. So my Kadeira-Spencer theory is a theory governing some differential forms on my Calabi-Yau, and on a product space, the polyvector fields factorizes as products as well. So dimensional reduction, as usual, is going to be an instruction to keep only the massless field content of the theory, which in the twisted context is going to tell us that we should restrict to considering harmonic polyvector fields on T4, which by this isomorphism here tells us that we're keeping, well, harmonic forms. So in other words, when we do the dimensional reduction, we just pick up a factor of the cohomology ring of T4, and that will kind of come along for the ride in many of the computations. So the cohomology ring of T4 has 4 free generators, DZ1 through 4, and I'll just label them, I'll rename them as etas, just to emphasize that these are some anti-commuting variables. They're going to span this flat supermanifold if you wish. Okay, so that's the result of the dimensional reduction. And as I said, we need to understand the back reaction in this theory, or the deformation of complex structure that's induced from the presence of these branes. So the RR flux in this case turns out to descend to a special polyvector field, in particular a Beltrami differential, and the equations of motion and constraints tell us that this Beltrami differential is in fact an integrable complex structure deformation away from the support of the branes, preserving the volume form. And one can write down this Beltrami differential explicitly. It depends in particular on the etas, and it also depends on this brane charge F. So it's an element of H2T4 of length n. Remember, n was the number of branes we had in the theory. So I have some explicit expression for the Beltrami differential. As usual, in a deformation of complex structure, I'm adding it to my del bar operator, and now I can compute. So we have a new complex structure, and I should ask now, what are the functions that are holomorphic with respect to the deformed complex structure coming from this Beltrami differential? Well, given the Beltrami differential, you can just compute it. The W1 and W2 coordinates, holomorphic coordinates, are still good holomorphic coordinates, even in the presence of this new field. And you can also solve for these 2 other new good holomorphic coordinates that I'm calling U1 and U2, which depend on the F's, etas, and the other coordinates in the following way. And by multiplying things together, it's not that hard to see that these coordinates satisfy the following equation in C4/4. And this is the defining equation for the superconifold. So this is the main punchline, or the upshot of this derivation, that the analog of ADS3 cross S3 is going to be the superconifold for us. And we call it the superconifold because had there been just an ordinary number or parameter on the right-hand side here, this would be nothing but the equation for the deformed conifold. But instead, because of our particular setup that involved T4, we have a dependence on these anti-commuting variables and this F. So we have some anti-commuting thing on the right-hand side. So this is what we call the superconifold. And we always restrict to the locus where not all of these U's and W's are 0 at once. So this is the basic thing that we want to study. We can now just compute things about Kadira-Spencer theory on the superconifold. And this is our twisted version of ADS. And we can start to make progress just studying this part of the duality. So I'm going to focus on the supergravity for most of this talk and defer to later work some of the details about the twisted CFT side or the vertex algebra side. Okay, so given this setup, what are some of the things one can compute with this theory? Well, first, there is one technical point that I want to emphasize from the outset, which turns out to make life very convenient computationally and was also surprising to us when we first realized it. So before we took into account the complex structure deformation, this is our flat transverse space. We have C3 with the support of the branes removed, and we have this factor spanned by the etas coming from the dimensional reduction, which corresponds to setting f equal to 0 on the previous slide. That's the flat space answer. So if we had wanted to study Kadira-Spencer theory in the absence of back reaction, that's the setup we would study. However, on the superconifold, we have these f's and etas on the right-hand side, and f cubed is quite clearly 0 in the cohomology ring of T4, which tells us that the effect of this back reaction can only correct flat space answers by a finite number of terms. So there's some kind of truncation happening here that would not happen, for example, in the ordinary deformed conifold, where you would get asymptotic series and in 1 over n, correcting the flat space relative to the back reacted answers. And again, this is going to be a huge boon for us computationally. Ordinarily, if we wanted to study this open closed string system, maybe we'd write down a vertex like this to approach things Feynman diagrammatically. Had we wanted to do perturbation theory, we'd have the brane coupling to some closed string fields in Kadira-Spencer theory via this Beltrami differential. And a priori, you would expect that to capture something like a propagator in the back reacted geometry, you'd have to do some kind of resummation or hope that you could of some diagrams like this, where you would have a priori an infinite number of these flux legs correcting the computations. But here we can have at most 2 such legs if we wanted to compute such diagrams. So that's just something I want to stress, which I think a priori is surprising, but certainly quite nice for our purposes. Okay, so we have this Kadira-Spencer theory that's somehow perturbatively close to flat space in a technical sense. And well, what are some of the properties that this theory has? In particular, one of the most basic things that you might want to determine are the single particle gravitational states in Kadira-Spencer theory on this superconifold. So we'd like to enumerate all such states up to gauge equivalence and see what kind of answers we get, and in particular, if they comport with the physical with BPS states in the physical supergravity. So one can use geometric techniques to approach this problem. I won't give the details of these computations, but in particular, we closely follow some methods that were developed in a paper by Costello and Gaiotto, also studying an example of twisted holography. And many of the techniques they developed can just be adapted directly to this case. So I'll refer to that paper and our paper for the details of this kind of computation. The basic idea is to study a compactification of the superconifold, which has some explicit boundary geometry, and then ask, given my Kadira-Spencer theory, I have some equations of motion, I can impose some natural vacuum boundary conditions on the fields, and I'd like to ask that the single particle gravitational states, as usual, should be dual to local violations of the vacuum boundary condition that otherwise satisfy the equations of motion and the boundary conditions everywhere except at isolated points. So again, one can do this analysis. Let me just tell you the upshots and the basic takeaways from what we find. So we find some particular states in Kadira-Spencer theory that I'm going to name alpha, gamma, and some mu's. Alpha and gamma are fermionic fields, and the mu's are bosonic fields. So first of all, it turns out we can write explicit closed form expressions for these things. I haven't fully done it on this slide. And in particular, we're really aided and abetted by this truncation property from the previous slide. But I'll refer to the paper for the explicit expressions of these things. Importantly, all of these states turn out to be highest weight states for an SL2 and an SU2 algebra, which have natural geometric interpretations from this point of view. So they're represented by some vector fields on this boundary. You can act on the states and see that they're highest weight states of the listed quantum numbers here. Their descendants with respect to these algebras are also included. You can also write them down explicitly. They're part of the story. And all of these fields occur, as you might expect, with a multiplicity depending on the cohomology of T4, which again is technically coming along for the ride in all of these computations. And the key point here is that these states organize into some very familiar objects physically. They form certain multiplets. In particular, they form short multiplets with respect to the superalgebra PSU112. And this superalgebra is perhaps familiar to some of you as the global subalgebra of the n=4 superconformal algebra, which is enjoyed by the boundary CFT. In particular, in a holomorphic twist, the boundary CFT only has one holomorphic copy of n=4 superconformal algebra, and it has so as its global subalgebra one copy of PSU112. So these fields in a holomorphic twist are organizing themselves naturally into short multiplets, and this is reassuringly exactly what we expect to obtain from classic papers of de Boer and David Mandel-Wadia. So that is comforting that our twisted theory indeed seems to be capturing information of a special subset of the untwisted theory. Here's another result about Kodaira-Spencer theory on the superconifold that you can prove geometrically. Again, I'll refer to the paper for the details of the proof, but it's not a hard result at all. So you can prove that there is a nice infinite dimensional symmetry algebra, in particular Lie algebra, acting as the symmetries of gauge symmetries that preserve the vacuum in this theory. And I'm working in the strict supergravity limit again, so this is a purely infinite n result. As a vector space, the algebra looks something like this. Maybe it looks a little bit forbidding, but it's explicitly described in terms of some very concrete geometric objects. You can also write down the commutators and anti-commutators completely explicitly. The interesting part is that the bosonic piece of this infinite dimensional algebra is the algebra of holomorphic divergence-free vector fields on the superconifold. This algebra is an algebra of symmetries of the superconifold. And here's some fermionic superpartners that I'm going to not worry about today. Okay, so this is our infinite dimensional Lie algebra. It acts as vacuum preserving gauge symmetries of my gravitational theory. Holographic duality then will suggest the following natural conjecture. What I have on one side must act somehow on the other side. So in particular, we conjecture that this Lie algebra should act on the chiral algebra of the SimN-T4 superconformal field theory in the strict infinite n limit. And what this symmetry algebra is dual to is what's called the global symmetry algebra of the CFT, which are the symmetries that preserve the vacuum at 0 and infinity. So just as SL2 is the global symmetry algebra of Virasoro, just as PSU11/2 is the global symmetry algebra of the n=4 superconformal algebra, we conjecture that this infinite dimensional Lie algebra is the full global symmetry algebra of the full chiral algebra in the holomorphic twist. Good. So in particular, it must include PSU11/2 among the low-lying modes, because that's the global subalgebra of n=4. And indeed, you can explicitly find that algebra here, although I haven't shown it. But again, it's not a difficult computation. And it includes modes of all of the other fields, so it's much larger. In particular, it includes the appropriate modes of the alphas, gammas, and mu's of the previous slide. Just as a remark, this is a very nice geometric algebra. It's related to algebras of functions on the superconifold. Algebras of functions on the ordinary conifold have appeared previously in string theory, in work originally by Witten, and then in a line of thought that was pursued by others. And in that case, these algebra functions on the conifold arose as the ground ring in a certain non-critical string theory. So some degree 0 cohomology elements that generated an interesting and I think unexpected symmetry structure in a string theory. So just a remark or a question for the future is, could the ground ring of the ADS3 cross S3 cross T4 string perhaps be related to the algebra of functions on the superconifold? I think it would be nice to make connections between these objects, but that's just a question it's food for thought. So let me tell you the situation thus far, just to summarize some of these results. So far I've told you that studying twisted supergravity in the sense of Costello and Lie gives for our bulk or ADS theory, gravitational theory, Kodaira-Spencer theory on the superconifold, employing this twisted derivation. You can use algebrogeometric methods to enumerate the single particle states, and they organize themselves into precisely the representations expected from the familiar physical duality. And you can also determine the infinite N, or purely classical supergravity symmetry algebra, and it's determined in terms of geometric objects. So more generally, you would like to, at least at infinite N, start to study the full vertex algebra, not just its global symmetry subalgebra. And if one were to do this from the gravitational point of view, there's a prescription that one would follow. You would try to extract these OPE coefficients from Witten diagram computations in Arcadira-Spencer theory, and then try to match them to 2- and 3-point functions in the twisted CFT. And it's a healthy exercise to do this, at least for some OPE coefficients. And I will not say anything more about that. It will appear in the future. And in particular, although you can do this and do this matching, it's a tedious procedure. Even in the holomorphic theory, it's a tedious and technically difficult procedure. So it's not really the front on which we want to push this the studies of this toy model. But okay, it seems that in our hands, we still have a nice toy example of the ADS-CFT correspondence. It seems so far to be amenable to rigorous formulation, at least then. The untwisted counterpart is well studied. And now for the remainder of the talk, what I'd like to do is try and ask what kind of mathematical structure we can really glean that's underlying this twisted duality, and what can we learn from it. So this is the part of the talk where Cazul duality enters. And in particular, it's going to be useful for us to also obtain some results beyond the strictly planar limit, or in particular, we're going to be able to access 1/n corrections at the end of the day. And of course, part of the motivation for trying to study the mathematical structure here is we hope that some of these structures will be able to apply to or lend insight to at least twisted dual pairs a little bit more generally, perhaps even serving as a defining principle for these special examples. At least that's part of the hope, but to be determined. So what's Cazul duality? Well, it's some kind of operation that given an algebra A, one can obtain a different algebra A shriek. For the moment, A and A shriek should be thought of as differential graded associative algebras, or if you really wish, A infinity algebras. So they're algebras that are actually better thought of as complexes with a differential. A and A shriek share various nice properties. In particular, there are equivalences among their module categories that are very nice. But so given, the important point for right now is that given A, you can define a natural object A shriek, and I'll tell you that in fact it has a natural role to play in a physical system, that these Cazul dual pairs naturally emerge from a physical setup. So at the moment, this seems like a little bit of an interlude, but I'll come back around to ADS CFT shortly. So A shriek can be defined in terms of A in the following way. So let's say A is an algebra or a DG associative algebra over C, and we'll view C as a one-dimensional module for A, the ground ring of the algebra. Then A shriek is defined in terms of derived endomorphisms of this one-dimensional module that commute with the action of A. Or loosely speaking, there's some homomorphisms from C to itself, compatible or commuting with the action of this algebra. And you can see directly from this definition that indeed I'm really working with complexes. Even if A was an ordinary algebra supported in degree 0, A shriek kind of has no choice but to be a complex. Well, physically, I've already sort of anticipated where natural complexes might arise. We have BRST complexes, or in this context, twisted BV-BRST complexes, and we have a natural differential coming from our twisted BRST operator. And indeed, Cazul duality does appear in physics. In particular, it arises when one tries to couple topological line defects of order type to bulk quantum field theories. So what do I mean by that? Well, let's say I have a topological line in some quantum field theory, a topological direction, meaning that there's some operator in the theory whose anti-commutator with the BRST operator renders translation along that direction trivial in cohomology. So in other words, if I bring operators from my bulk theory to the support of this line or very close to it, they should acquire the structure of an associative algebra, because in the presence of the topological twist, I don't care what the precise positions of the operators are, I only care about their ordering. That's the structure for an associative algebra. The claim is that given defining A in that way, as that kind of associative algebra, naturally produces A shriek in terms of coupling this line defect to a bulk quantum field theory. So let me be precise about that now. So we say that A shriek is, if you wish, the algebra governing the universal line defect in my theory. What do I mean by that precisely? Well, a topological line defect of order type means I'm just trying to couple some topological quantum mechanics along the line to my bulk quantum field theory. And I wish to do so in a BRST invariant way, or in a way that's free from continuous gauge anomalies. So my topological quantum mechanics, it's my choice. A priori, it supports some arbitrary algebra of operators B that also has the structure of a DG associative algebra. And I claim that anomaly-free or BRST invariant couplings of the topological quantum mechanics to my bulk theory are in bijective correspondence with a choice of homomorphism from A shriek to B, where A shriek was defined on the previous slide. In other words, A shriek governs the symmetries that a defect theory needs to have to couple non-anomalously to my original theory. So just as when you go to a carnival and you see a sign that says, you must be this tall to ride this ride, A shriek is telling you that whatever the generators of your B algebra are, whatever larger algebra or whatever algebra they fit into, they had better furnish a representation of A shriek. They had better have at least that much symmetry in order to couple to my original theory along that topological line. The proof of this statement is in the paper. We proceed by a path integral argument. In the interest of time, I won't flesh out the details. But ultimately, these path integral manipulations produce for you a Moore-Cartan equation, and one is able to relate these possible couplings as a space of solution up to gauge equivalence to the Moore-Cartan equation of these tensor product algebra along the line. So here intuitively, we see something like, well, deformations of an uncoupled tensor product algebra will give us a space of possible consistent couplings. And you can make use of a very deep isomorphism in mathematics that tells us that this space is isomorphic to the Hom space, maps from the Cazul dual to B. Okay, so this is something general. Okay, that all seemed like perhaps a bit of an interlude. How do these ideas relate to the ADS-CFT example that I was discussing in the earlier part of the talk? Well, what I'd like to do is generalize this notion or propose a generalization of this notion of Cazul duality to the context of vertex algebras or differential graded vertex algebras. And let me do this physically by proposing an analog of the previous procedure to the vertex algebra context. So mathematically, this has only been formalized in some special examples by C. Lee, so it's something that hopefully we can work on with our mathematical colleagues. The basic idea is to make the obvious replacements. We go from a topological line to a holomorphic plane, an associative algebra to a vertex algebra, commutators become OPEs, and again, the line becomes a holomorphic plane. And then let me define now a Cazul dual algebra A shriek as kind of the universal vertex algebra that can be coupled to my bulk theory along a holomorphic plane, such that there are homomorphisms of DG vertex algebras from A shriek to B that govern the possible BRST invariant couplings along that plane. And well, why is this notion something I want to introduce? Because remember, in my twisted theory, this derivation was really remembering the origin of ADS-CFT as a coupled open closed string system. And at the most naive level, I can imagine my two-dimensional D-brane theory as defects of order type in flat space coupling to my closed string degrees of freedom. And remember, the twisted theory doesn't care so much about these precise decoupling limits. So the question is, given our now good understanding of the theory in the bulk, what we understand about Kodaira-Spencer theory on the superconifold, can we deduce something directly about the boundary chiral algebra, about our twisted SCFT, using this Cazul duality perspective by demanding the vanishing of anomalous couplings between the two? Now, of course, thinking of D-branes just as defects in the flat space theory is naive, and I will have to incorporate back reaction later, and it will deform the notion of Cazul duality that I need to use. Sorry, I see some chats, but I don't think it's easy for me to check them. So if it's a time warning,
yes.
Yeah,
so I think you have officially 2 minutes.
2 minutes. Okay.
5 minutes.
Great. Okay. Yeah. Thank you. I'll wrap up. Okay. So that was a fairly abstract thing that I've said so far. Of course, I believe that formalizing these things will be useful for many reasons, but at some point you just have to get down to brass tacks, and let's compute the chiral algebra or the Cazul dual algebra from my bulk theory, from my Kodaira-Spencer theory. Given A, I can compute A shriek and vice versa. Let's do it physically. So I can write down general BRST invariant couplings between Kahler-Spencer theory and a putative defect CFT. Here I've displayed one, coupling one of these mu fields to some so far arbitrary defect operators J. In particular, some of these J's correspond to chiral primaries or highest weight states of those multiplets, just to orient the physicists that might be familiar with those operators. And let's, again, for the moment, pretend I can work in flat space and work at infinite n. Well, I can just associate Feynman rules to these couplings, write down Feynman diagrams, compute the BRST variation of the Feynman diagrams, demand that all these BRST variations cancel, so there's a net no anomaly, and ask what conditions those impose on the OPEs of the defect operators. So writing down such tree-level diagrams will correspond to computing the Cazul dual at infinite n. But in principle, you can also write down loop diagrams, compute quantum corrections. In general, we know there can be gauge anomalies at higher loop order, and these will deform the classical OPE to some quantum corrected algebra. So here I've just listed some tree-level diagrams, and I've displayed exactly what one gets from performing this computation at infinite n in flat space for these J operators. Oops. Oh, sorry. There we go. For these J operators. Again, of course, it's not the whole story, but we can compute. And the J's in particular give some nice superloop algebra that also has a nice geometric interpretation as well. And again, in principle, you do the same kind of computations for the other operators, and you can proceed at order by order in 1 over n. This is my last technical slide, so never fear. I do have to tell you about back reaction because that should, again, modify the story in some way. D-branes are not just defects in flat space. They source fields that interact with my closed string theory. In particular, there's going to be some additional term in the bulk action that couples the Beltrami differential field to closed string fields in the Kahler-Spencer theory. You can write it down and you can compute the BRST variation of that term. And it is non-vanishing. And it's non-vanishing precisely on the support of the D-branes. So previously what we had done is try to compute the vertex algebra or defect OPEs by demanding that the coupling of the defect to the bulk theory had vanishing anomaly. Now in the presence of back reaction, we also have to reckon with this term, but technically we can do the exact same thing. We just demand that the defect OPEs have an anomaly that precisely cancels that of the anomaly from this term, so that the total system, again, is BRST invariant. And there's a suitable Feynman rule, again, that one can write down for this term. And cartoonishly, it looks like a vertex like this, where the Beltrami differential is coupling to the identity operator of the chiral algebra. And again, here, the beauty of this truncation saves us, because so far I had been working in flat space, but because f cubed is 0, there's only a finite number of new diagrams incorporating the back reaction that I need to write down at each order in 1 over n. So life is fairly simple. In the n goes to infinity limit, it turns out that there's 3 classes of diagrams to compute. I'm just giving you the simplest one here. And in particular, this one centrally extends the algebra. And again, there's some other diagrams that you compute. So I think there's a hope because of the simplicity of this model and this truncation. You could hope that perhaps we can even prove some all orders results about the OPEs using homological algebra techniques, but doing so will require some interaction with mathematics and will in particular require formalizing this version of Cazul duality for DG vertex algebras. In the presence of back reaction, it should be some kind of version of curved Cazul duality, which roughly speaking adds a source to the Morar-Cartan equation. So now let me summarize and wrap up. So for this part of the talk, I've said that there's a version of curved Cazul duality for vertex algebras that comes from considering anomaly-free bulk defect couplings. You can compute the defect algebra from the bulk or vice versa, diagrammatically in order by order. And again, the key point is that the defect operators had better furnish a representation of my Cazul dual algebra. For BRST invariance, that's non-negotiable. So you are directly accessing at least some kind of universal part of the boundary chiral algebra by doing some computations with the bulk fields, which are some complex of ghosts and anti-fields, but you can work with them. In our ADS-CFT context in particular, if you fully incorporate the back reaction at infinite n, which I just gave you a small preview of, you can recover that geometric algebra we saw in the earlier part of the talk from this Cazul duality point of view, including these divergence-free vector fields. And again, in particular, that global subalgebra, our old friend, does appear in the low-lying modes. So that works nicely. And moving beyond the global subalgebra in particular produces, among the larger algebra, an n equals 4 superconformal algebra. I showed you how the central extension comes about. And One, of course, should and must move beyond infinite n, which involves, again, just computing finitely many new classes of diagrams, and hope to present some more results on that in the future. So that's what I wanted to tell you about today. I think this is just the beginning of a much larger story. And of course, there's, as with any story, there should be quite a lot of sequels, and there's much left to determine. So let me list some here. I don't think I'll, in the interest of time, since I've already gone over, I won't go through things explicitly. But for example, perhaps in Kadira-Spencer theory, it would be very interesting to know if we could perhaps study some BPS black hole solutions, recover other aspects that are known from the boundary CFT from the Kadira-Spencer point of view. It would be wonderful to connect the twisted supergravity perspective with various worldsheet analyses that have been performed in recent years. There are a lot of beautiful results on that front that it would be great to connect to, and much more, including other examples. And again, towards at least an optimistic goal of proving special examples of the ADS-CFT correspondence. So thank you for your attention. Thanks for your patience since I went a little bit over time. And yeah, I'll take questions now.
Hey, thanks very much, Natalie, for this nice talk. I'll unmute everyone. And so please clap. And I will mute everyone again. So there are questions by, I think, Mykola Dedushenko. You should be able to unmute yourself without me doing so.
Hi, Natalie. Nice talk. So I have a few questions, actually. So the first one is, from the point of view of Kadira-Spencer theory, how do you determine the vacuum boundary conditions?
Oh, there are natural choices of those. It's part of a longer story. Again, the paper of Costello and Gaiotto has the most complete analysis that I would refer to for the details.
Yeah, I mean, I know they have this kind of logarithmic poles. I'm just wondering what kind of principle, physical and or mathematical, would allow you to fix those poles, for example?
So in particular, one has to ask that the interactions in Kadira-Spencer theory are still well defined at the boundary, given the holomorphic coordinate system on the boundary and the form of the holomorphic volume form as one approaches the boundary. So given consistency conditions from that, one also has to show that there's a sensible propagator and various other things. So yeah, it's a bit intricate and involves, well, it incorporates in particular well-definedness of the interactions and bulk to boundary propagators. Although if Kevin and Davide have want to chime in and add to that as well, please feel free.
Okay. Another question was about the 1/n corrections in the case of ordinary conifold. So what would be the simplest quantity to receive such? I mean, certainly the geometry itself, the background already satisfies Kadira-Spencer equations, so it's exact, right? But what would be the quantity that receives, like the simplest example that receives 1/n corrections?
The simplest example that receives, well, so for example, I mean, we're computing 1/n corrections in the vertex algebra for this defect theory. Or do you mean something else? I mean, you could imagine doing scattering processes of these single particle gravitational states. Well, first of all, the form of the gravitational states themselves receives 1/n corrections. In our example, they truncate because of this f³=0 property, but in the ordinary conifold, the form for the alphas, gammas, and mu's and so forth incorporate or involve 1/n corrections. Their scattering processes would involve 1/n corrections.
Okay, so the structure constants of the chiral algebra, basically.
Yeah, absolutely.
And one last question, similar actually in spirit. What would be the simplest example of causal duality in the chiral algebra? Like for associative algebras, probably one of the nicest examples are quadratic algebras, where you can explicitly describe them.
Absolutely, yeah. Quadratic algebras in the associative case are very nice.
So what about chiral?
The simplest, yeah, that's a good question. The simplest. In our paper, we do an example of holomorphic Chern-Simons theory, but I would hesitate to call that the simplest. It's just kind of a slightly simpler analog of the computation in the Kahler-Spencer theory. Actually, there may be. I would refer to that paper by Seeley that I cited earlier, who was working on formalizing this notion of causal duality for chiral algebras from a more Cartan point of view. And I'm blanking on some of the precise examples that he studied, but yeah, that's where I check.
Okay, Greg Moore has a question. Greg, if you can unmute yourself.
Hi, Natalie.
Hi.
Hi. So, yeah, I had a question about this equivalence between the Morey-Cartan elements of A tensor B and the Ham from A shriek to B.
Mm-hmm.
Does that mean that the set of Morey-Cartan elements is a linear space?
The set of more Cartan elements is a linear.
Well, Ham A shriek, well, at least the way I was thinking, maybe you mean, I don't know what you mean by Ham, but I assumed you meant by homomorphisms of algebras.
Mm-hmm. Yeah.
Right. That's a linear space. I think of the Morey-Cartan elements as sets of solutions to a highly nonlinear solution. So I don't think of that as a linear space. So I was a little confused by that.
Good. Maybe let me think about that a little bit and get back to you.
So another question about that statement is that were A and B algebras or A infinity algebras?
You can think of them as A infinity algebras. I was thinking of them as DG associative algebras, augmented algebras actually, which is something I suppressed.
Okay, because taking a tensor product of two general A infinity algebras is not a trivial thing at all. In fact, it's a moduli space of tensor products.
Yeah. So
the moduli space would have to show up on the other side.
Yeah. So in that isomorphism, I was lying a little bit for simplicity. In the context of A infinity algebras, yes, you, strictly speaking, rather than A tensor B, you have actually the augmentation of ideal of A tensored with B. Yeah, there are many things I swept under the rug, but I think actually sorry.
But the notion of what I'm getting at is the notion of a tensor product of A infinity algebras is non-trivial. And in fact, there's not really a canonical tensor product.
Yeah, I was being a little bit sloppy there. There's actually the subtleties of that definition, I think, were discussed nicely and fairly recently in a paper by Gaiotto and O.
Okay.
But yeah, indeed, that equation that I presented should be viewed as a cartoon, and we can
okay.
discuss.
And last question about that equation. Yeah. So you want to generalize algebras to vertex algebras, did I?
Yeah. So I need.
By vertex algebra, you mean vertex operator algebra?
Not necessarily. I just mean some differential graded vertex algebra. I don't think I need the extra conditions from a VOA. Okay. But I do need to tell you what MC of A tensor B is, and it's not really on that side. It's not a tensor product of vertex algebras. You should define some suitable Lie algebra related to that tensor product. Again, it hasn't been fully formalized except by Seeley in special examples. But the basic idea is that given those uncoupled vertex algebras, you should define some kind of Lie algebra that, roughly speaking, is going to be from looking at the coefficients of 1 over z in the OPE and quotienting out by total derivatives. So you have to define a suitable Lie algebra from the tensor product from the vertex algebras. Otherwise, that thing doesn't make sense. And I haven't told you how to do it. And it hasn't been done in general, only in examples.
Okay, thank you.
Okay, Coleman, you have a question, please.
Yes, very nice talk, Natalie.
Thank you.
The conifold, the super conifold that you had depended on Fij, which I guess is related to the B fields on T4, correct?
Yeah, it's essentially the brane charge. So the integral of f squared over C0/4, the direction spanned by the etas, is n. So it's just encoding the flux of the D-branes.
Oh, just the flux.
Just the flux.
Those discrete parameters for you.
Yeah. Well, so since I'm working in classic. Oh,
right. Sorry. So the main question is motivated by where does the moduli of T4 enter your story?
The moduli of T4 essentially don't enter my story. The Kadeira-Spencer theory was only, so first of all, it's only sensitive to the cohomology of T4. So I really only use kind of the basic, like the Poincare pairing and the cup product in H star of T4. And since I'm working classically, it's H2 of T4C. So the dependence on T4 is that of just perturbative classical supergravity. There's not any finer information retained after I do the dimensional reduction.
So, I see. So it seems to me that there are two possible views of topological theories applied to this example, ADS3 times S3 times T4. One is viewing ADS3 times S3 as if it's a Calabi threefold, and viewing T4 as the extra space, which is so it's reversing the order of what we usually do.
Yeah.
Which is fine, and I think that's closer to what the viewpoint you have taken, at least closer to the viewpoint you're presenting here. There's another viewpoint, which is you start with the theory on T4. And in that context, the theory has more supersymmetry than Calabi-Yau. And it's natural in that case to do the n equals to 4 topological string version of it, which is not Kadeira-Spencer theory, but gives you a self-glow gravity in 4 dimensions as the corresponding theory. So there would be a generalization of that presumably for these extra ingredients that you're introducing, but in that theory, it would depend on the moduli of T4 and all the other.
Yeah.
So I'm curious to know if you have had any thoughts about that other topological twist.
No, that's an excellent point. One slightly related thing that I've thought about, but don't have anything too concrete to say about is that one could also, as you said, we can start from the theory of branes on T4. Now, view that as a gauge theory in the ADHM sense, in which case N1 and N5 start being treated asymmetrically as opposed to completely symmetrically as they are from our point of view. You could study a twist of that gauge theory, which should now treat N1 and N5 differently. And sort of how does that theory differ or remain similar to the analysis that we did, which is dual to the pure supergravity point. I guess that was a long-winded way of saying that is an excellent point that I wish I could say more about. It's indeed something to think about and should be physically very instructive for understanding these examples better. I agree, but unfortunately don't have too much more to say at the moment. It would be great to make the connection more.
Okay, I don't see any other questions. So I think we close the session. Let's thank Natalie again. Unmute all.
Thanks, everyone.
And I think Jeff presumably will take over now. So I'll leave you with Jeff. Thanks, Natalie.
Thank you very much, Sakura and Natalie, and I really appreciate the background. Let me thank the speakers for the day and also the session chairs for the day. I have been assigning people to the breakaway rooms in the background, and I'll still do so for anyone who has any preferences to go to session 1, which will be the first 3 speakers for the day, or session 2, which would be Tom and Natalie in their session. The speakers will be assigned automatically to their sessions so that they can answer questions and things like that. I'd like to take the opportunity to encourage students in particular to go to the breakaway rooms and ask questions. It would be a good experience to interact with the speakers. So if you could please just tell me your preferences for which session to go to. I will include that and then open the rooms on the hour, and I'll keep them open for an hour, after which we'll close for the day. So thank you very much to the speakers again and the session chairs, and let me know your preferences, and you should get an invitation to go to a particular breakout room on the hour.